Hello, everyone, and welcome to the Montréal A.I Symposium. We have over 1,000 registrations for today. This is super exciting. I am Audrey Durand from Université Laval and Mila, and I'm very happy to be chairing this virtual edition along with my amazing co-organizers, Erdem Oskan from Automat. Hi, Erdem.
Hi,
Amy
everyone.
Zhang from Mila and Facebook. Hello, Amy. Pablo Samuel Castro from Google.
Hello. Hello, everyone. I'm Pablo.
Hello. Tess Berthier from Imagia. Hello, good morning. Prudencio Tosu from InVivo AI.
Hello, everyone.
Hi. And last but not the least, Nadine Kairala from Mila. They did a wonderful job at putting this event together. If you like today's symposium, you should thank them. If you hate it, please blame it on me. And before I lay down the schedule for today, I want to thank all our sponsors. Without them, there would be no Montreal AI Symposium. So I invite you to check out their virtual booths in Gathertown during the poster session. You know about this already if you went for a virtual coffee this morning. Yes, 2020 is the year of virtual coffee. So most of today will happen here on Zoom. The whole schedule is on the website, but essentially you'll find 3 invited keynotes with live Q&As, a panel this afternoon on ethics, fairness, and bias in AI, and poster spotlights to give you a foretaste of what you'll find in the virtual poster session at 3 p.m. The virtual poster session will happen on Gathertown. You have received the link this morning and yesterday from your Eventbrite registration. Gathertown is also accessible all day if you wish to walk around during the breaks. You can re-enter the Zoom session from one of the rooms in Gathertown or by using the same link that you got from Eventbrite. So I think today will be a great opportunity to see what has been happening in the Montreal AI ecosystem, but more importantly, in the whole Québécois AI ecosystem during the past year, considering how isolated we have spent the past few months. I strongly invite you to actively participate in today's event. You should use the Q&A tool in Zoom to ask questions during the live Q&As with keynote speakers and during the panel. If you're watching through the YouTube stream, you can send your questions as a YouTube comment, and we'll make sure that it makes its way into the Zoom Q&A tool. Your participation will greatly shape today's experience. So without further ado, we'll start with messages by 2 of our sponsors, Samsung and Coveo, followed by a short break before we kick off the day with our first keynote.
So Sail Montreal is bringing fresh ideas from South Korea.
I'm very excited about the creation of SAIL, which is a new academic-style research lab wholly located within Mila, which makes it very unique. We're hiring research scientists to do open science in collaboration with the Mila ecosystem, as well as visitors from SAIT in Korea.
What I expect is that there would be a lot more research collaborations, a lot more exchanges, events that will happen that will increase the amount of cool new research that's being done by both labs.
I hope that the collaboration with Mila, which actually started a few years ago, will continue. I think on the theoretical side, Simon is an amazing researcher and he's recruiting very strong theory people. But I think the collaboration also leads to practical applications, which otherwise we wouldn't have a chance to do.
A lot of companies have started a lab together with the Mila, such as Microsoft, Google, and all the other places. But what we see is that those are all US companies only. And then what I believe is that the SAIL, which is the AI lab of the Samsung Advanced Institute of Technology, can bring another perspective. I believe this kind of diverse view is going to be the thing that's going to make SAIL really great and also Mila great as well.
So I hope that the SAIL lab will inspire us to bring us new insight.
It's contributing to the AI hub in Montreal, the AI ecosystem. It's great to have companies like Samsung that can have a huge worldwide impact with their products. embedded in Mila.
Coveo is a born in Quebec unicorn. Having raised $227 million in 2019, Coveo's pioneering approach to AI-powered search and recommendation rocketed our valuation past $1 billion. People interact with Coveo technology every day on leading customer, corporate, healthcare, and government systems. Our built-in Quebec technology brings the most relevant and personalized information where it matters most, whether it be at work, shopping online, or during customer service interactions. In AI, Coveo develops state-of-the-art personalized algorithms for NLP, revenue optimization, question answering, recommendation, user profiling, document classification, and much more. The better part of it, we work on real data in real systems that people use every day. Imagine, your algorithms can be used by more than 20 million times in a single day. Coveo has over 500 professionals that are passionate and driven by innovation and excellence.
All right. Well, it's 9:20, so we will continue with the program. It's my great pleasure to introduce my colleague Natalie Schluter, who's a senior research scientist at Google Brain and associate professor in NLP and data science at the IT University in Copenhagen, Denmark. Natalie's primary research interests are in algorithms and experiment methodology for the development of statistical and combinatorial models of natural language understanding and generation, especially under computational hard settings. Natalie is currently serving as equity director for the ACL and serving as ACL 2020 co-program chair. Natalie's Canadian, so this fits well with the Montréal A.I Symposium, but she currently lives in Copenhagen, and she's been living there for the past 10 years with her 2 daughters. So it's my great pleasure to introduce her video, and I hope you all enjoy it as much as I will.
Thank you. Hi, my name is Natalie, and I am coming to you from the NLP world. I'm going to talk to you today about some tough and strange problems in automatic summarization of documents. So I had my first experiences in research in automatic summarization about 5 years ago when I was a postdoc. So I went over to the law faculty and I was working on this project called From Dogma to Data, and this was run by Henrik Palmer Olsen. And it was a project that was looking at the dynamics of decision making or use of the Articles of Human Rights and decision making in the European Court of Human Rights. Now, lawyers or legal scholars, they're kind of the first sort of data scientists that there were, I think, except they don't use machines necessarily, they just read everything. So I was involved into this project because they had heard that with NLP, they wouldn't have to read these enormous 60-page, very dense documents of legal text, that instead they could just run an automatic summarizer and out would come these summaries that they could use to quickly determine whether the contents of this document was interesting or not. So this is what they had planned on using in order to quickly ascertain the contents of legal judgments from the European Court of Human Rights. So my background before this was mainly in parsing. That's where you take a sentence, you look at the words in it, and you get a machine to quickly determine how words are related in that sentence and go together to make up the meaning as a sentential unit. I'd also done some work in keyword extraction, so that's where you get a machine to extract the sort of most representative words of a document. This was really important for indexing, and it can be used as a sort of summarization. So enter my work as summarization. The first thing I do is I find out what are the state-of-the-art machines in summarization. So the plan was just to run these and use it as like my starting point. So the lawyers were really excited about what this could do and really wanted to see what the output of these state-of-the-art NLP automatic summarizers were like. Okay, so this is from a state-of-the-art automatic summarizer. Now this is over not legal text, but just newswire articles, which are very easily accessed. They're very publicly available, so a lot of NLP work is done over newswire text. Now, here is an output summary. Let's have a read together. There were kryptonite locks and leaflets from the army of God and the lambs of Christ. For many in the FBI, that's a problem. Violence at abortion clinics is only part of the problem. The slaying of Dr. Barnett Slepian in his home last week eliminated the mainstay of the only abortion clinic here, but it has not eliminated women's access to abortion. Slepian was one of only a handful of doctors in Buffalo who were still willing to perform the procedure in the face of pickets, protesters, and threats. In contrast, James Charles Kopp, who is being sought as a material witness in the killing of Slepian, left a trail of clues about his motives. Now, in reading this summary, I mean, you get a good idea about what the topic of the original article was. I mean, it is about the slaying of a doctor who carried out abortions. But in fact, the article is more about the concern of the FBI in a rising problem and how they're going to attack this. Now, there are some hints of this theme of the original article here. So, I mean, you could say that this summary is okay. It's okay. It kind of misses the original idea, but you get an idea of what the original article was about. Now, let's go over to the legal domain. In the legal domain, a judgment contains, so a legal judgment, at least at the Court of Human Rights, the European Court of Human Rights, contains the context of the legal case, so who's involved and what's happening, what are the complaints. And then it contains a description about how the articles of the Convention of Human Rights, how these were applied in making the judgment for the case. And it also cites some precedent, other court cases that used the articles in this way, and can kind of build up the legal context of the judgment. Now let's read this summary. As a consequence, Article 14, a provision which did not require a violation of the substantive provision of the convention, but only a link with it, was also applicable as the applicant failed to pay the fine on the 11th of June 1997. The registrar of the courts in Malta submitted an application to the criminal court in the case of Karl-Heinz Schmidt, in which only men were obliged to serve in the fire brigade or to pay a financial contribution in lieu of service, cited above, section 22. The court found that Article 14 was applicable and stated that it asked that court to summon the applicant before it and or to convert the fine imposed into a term of imprisonment. The applicant considered that the way in which the jury service had been imposed on him was discriminatory. Okay, skipping a little bit, I'll move to the end. Like the parties to the proceedings, the court considers that compulsory service, such as exists in Malta, is one of the normal civic obligations envisaged in Article 4, Section 3D. Okay, so I gave a whole pile of these sorts of summaries, which my boss, Henrik, had invited his lawyer friend to come and read in great excitement, and they were kind of appalled at what they saw here. So first of all, the text is very difficult to read. It's sort of a sequence of mismatched information. But if you concentrate really hard, you can see that there are some things that indicate what the original article was about. Okay, so we see that there's an application of Article 14. Great. We see that there is something about jury service that had been imposed on the applicant, which he thought was discriminatory in nature. And then we see that there is some decision that the court deems that there was no discrimination and that this is quite normal service. And then there is an Article 4, Section 3. Okay, now I think that in the NLP world, you might be, you might be tempted to think that this was kind of a success. Out of all of this text that was returned, we actually saw these bits in red, which were indicating what the original article was about. But for the lawyers, right, it would be highly risky to read this summary and determine that you had a good idea of what actually was inside the judgment. In fact, they would just have to read everything over and again. So I would consider, like, at this stage in its progress, automatic summarization is kind of relegated to the lab, and it's kind of just something that only NLP people get between each other. So I spent the next part of some years, and I'm still trying to figure it out, why this is the case, why with state-of-the-art automatic summarization tools, why we have the impression that they're actually performing pretty well, but when we look at the output and we try to apply them in the real world, that they're doing quite poorly. So we have this metric called Rouge, which is probably, even though recently it's been called into question quite a lot, and including by me, it continues to be the most used metric in determining the quality of output summarizations of our automatic summarization systems. So I'm going to show a few of my findings which indicate that this metric could be the reason why there is such a big mismatch between our lab work and the real world. Okay, so one thing that I noted that I will talk about is that based on some results, that perfect scores for extractive summarization are theoretically computationally hard to achieve. That we don't really have an idea of how what perfect is according to this metric, and that even relatively perfect scores, it turns out that humans cannot even achieve. So humans are bad at summarization according to this metric, and that very surprisingly, that state-of-the-art automatic summarization continues today to be unsupervised, and it is also pretty much without improvement for the past decade. So this is a paper that came out a few years ago showing finally what outputs look like across a number of baselines and a number of state-of-the-art summarizers. Now, a couple of the summarizers from this that were mentioned in this paper are still state-of-the-art today, but basically what this paper showed was that since 2005, that there have actually been no substantial improvements in the performance of automatic summarization for real world situations. So I thought I would just tell you what automatic summarization is. So suppose that we have this document. Well, in automatic summarization, you would just want to make some shorter version of this document, and it can be done in a number of ways. So one of the ways that it has been done, and this is where we are achieving the state-of-the-art progress is, which is from 10 years ago, is in extractive summarization. So in the extractive summarization type approach, you just decide, or the system decides which sentences are the most important, extracts these, concatenates them together, and calls that output a summary. Now, we also have a bound on how long the summary can be, because it has to be short. So generally, data sets come along with some description of some maximum output length for the summary. Now, since we're extracting sentences, when we're adding potentially greedily sentences, sentence after sentence to the output, we might go over this bound. So what people have typically done in the past is they just kind of chop off the last sentence so it appears within this bound. So here we have the last sentence, the Peterson. We'll come back to that chopping in a little bit. Okay, so more recent approaches for summarization have been neural, and in most of the more successful setups for neural summarization, there's a combination of copying words or segments and also generating new words or segments. So the system would read from left to right, copy a number of things, and then make the decision to generate new words along the way. So in this way, it is a combination of, extractive. It might not be full sentences, but it's still extracting words and phrases. The problem with neural summarization, and the reason why I won't be referring to it again in the rest of the presentation here, is that these systems are still not state-of-the-art. So there is a data problem for the neural systems. So summaries are very expensive to make. So there aren't actually a lot of documents that have summaries that are, handwritten by experts from the domain where the article or the text is coming from. So, if they were easy to come across, then obviously, like, for example, the legal judgments would have all have summaries already accompanying the legal judgments, but that's not the case. In the past, our summarization data sets have been pretty small, in fact, and that's not very good for neural networks. So in summarization for neural systems, the description of the original problem has changed. It started out with just title generation. So, and it would be title generation not from the entire document, or in this case, newswire article, but just from maybe the first sentence or the first couple of sentences. It could also be highlights extracted, just plunked out of the article and extracted, or it could also just be summaries that are, 1 to 2 sentences long. Now, the problem with this is that actually these are not general description of the summarization problem. So we still don't have neural systems that can make large summaries in any coherent way. So that's why I'm sidestepping the neural summarization road. So let's introduce to you the metric that is used, the central metric for evaluation of automatic summarization systems. And this is called Rouge. So it's called Rouge-N, where N is referring to the length of n-grams that are involved in computing this metric. So here, S refers to the summary that is the output of the automatic summarization system, and R is a reference summary. So this is a summary that has been manually written. It's a human-written summary. Now, in order to judge the output of systems, we look at an overlap of n-grams. So n-grams are sequences of n words. So a 1 gram would be, or a unigram, would be a word. A bigram or a 2 gram would be just a sequence of 2 words, and so on up to n. So we would have Rouge 1, which would be an analysis or an evaluation according to just like word overlap. Rouge 2 would be for bigram overlap, or the 2 sequences of 2 words, the overlap. So here's how to compute Rouge n. You take all of the n-grams from the output summary, all of the n-grams from the reference, you count up the overlap, and you divide it. You see how much there are contained in there. You divide it over the number of n-grams from the reference summary. That's it. And more recent years have claimed that a better evaluation is across multiple references, because people have different ways of writing. So let's use a multiple number of summaries and just take the average of this metric over the multiple summaries. Okay, so the first thing that I'm going to look at are, present to you is a result that actually maximizing for this Rouge metric is computationally hard. And then after that, I'm going to talk about perfect scores, relative perfect scores, and what's going on with supervision. Okay, so the result is that given a document, it's manually written non-extractive summary and the Rouge metric, n for some n, that building an extractive summary that maximizes this metric is NP hard. And to do this, I make a reduction from the max k dominating set. So if we have a graph, and in this case, I'm just talking about cubic graphs, that max k dominating set is a set of k nodes of the graph that are dominating or connected to the most other nodes in the graph. So this is an NP hard problem, and I am going to make a reduction over to building an extractive summary that maximizes the Rouge n metric. Okay, so as a starting point, we have a graph, which is a cubic graph, and the problem is to find the max k dominating set. What we need to do is make a document, and basically a document and a summary, which would, when you are finding the extractive summary with the best Rouge one, so ideally exactly the reference summary you would find again, that this would give you a solution for the max k dominating set in the original graph. So what we do is we use the labels of the nodes in the original graph as the vocabulary, and we make sentences by just considering the nodes in isolation as well as their neighbors. So this would be making a sentence here of 4 words. The dominating set here is described by the 3 red nodes that are highlighted in the original graph. Now, if we just make, so this is the original document, it just contains for each node all of the node and its neighbors in any order. And the summary, which would describe the max k dominating set, would be the sentences corresponding to those notes in red, for example. Okay, so this is the reduction. Now, I've only talked about Rouge 1, but this can actually generalize to Rouge 2 by just using a dummy symbol, so something that high-level set of the original graph. And I also have shown, like in general, for Rouge N, we just put between these word labels a dummy symbol n-1 times for Rouge N. Okay, so I've shown here that this is an NP hard problem to find output summaries that maximize Rouge because of this reduction. But if we use an Oracle summarization system that either exactly tries to maximize Rouge or greedily does, well, we should find that the greedy approach doesn't perform as well as the exact algorithm does. But this is simply not the case. So for the pretty classical data sets, which is the DUC04, this is also where this first summary that I showed you from Newswire, the article came from. We can see that the greedy approach is generally outperforming the exact approach. This happens on a couple other data sets as well, including this Wikipedia data set and the European Court of Human Rights data set that I had put together as well. Now, why is this the case? Now, if you remember when I was describing the approach to automatic not the approach, but the definition of automatic summarization in the extractive approach. Well, what happens was we would add a whole bunch of sentences, which is what the greedy approach does. It adds the best sentence at each round. And in the end, we might be over our budget of how long a summary could be. So we just chop it off. Now, the greedy approach benefits from this because it can make summaries exactly the length of the budget, whereas the exact approach might be missing a few words if there's no sentence that is short enough to fit within the budget deficit and the budget allowance. Now, this shows that the Rouge metric is not exactly telling us what's going on, because clearly adding 3 random words at the end of the sentence shouldn't be throwing off our understanding of the performance of the system to this degree. Okay, now as I was mentioning before, it has been suggested, since different people write in different ways, that it would be better to include multiple reference summaries and take an average of Rouge scores across that. So one thing that allows us to do is to check how humans are doing in their summarizing. So if we look back at the results for DUC, so DUC04, this top row, now, this is a data set that actually has the possibility to do this analysis because there are multiple handwritten summaries for articles in the data set. And we can see that the scores, these best Oracle summarizer scores, are up around late 40s, 50 for R1, and around 19 towards 14 for R2. Now, it turns out that if we evaluate one human summary to the remaining 3, that it turns out humans cannot summarize very well. So these are average scores of humans against other humans. So we humans are very bad at summarizing, but the machines are better, and that's even understanding what the machine output looks like, which is what I showed you in the beginning, right? Bunch of sort of nonsensical sentences stringed together. Okay, so let's move on to the right side where we have this graph. And what this graph is trying to capture is the distribution of vocabulary considering only a single reference summary versus considering all reference summaries at the same time. So there are a number, so the vast majority of all words that occur only in one of the reference summaries. And that's because, people write differently. But that also means that when a system actually finds one of these words and includes it into the summary, that it gets very little credit for doing so. In addition, it's impossible to include a word only 0.25 times. It's either in there or it's not in there. So this has an impact on best scores in automatic summarization. So no longer is it possible to get 100% because we cannot put half a word or 0.25 times a word into an output summary, which is what the Rouge score averaged across different references requires if you want to get perfect scores. Okay, so some concluding remarks about what I've just said so far. So we have the first time that, so from this paper that I wrote, which gave an NP hardness result for oracle summarization with the Rouge metric. But still, even though exact algorithms should be better, and apparently greedy should not be as good as an exact algorithm, that greedy seems to be doing just fine, according to Rouge. And according to the data sets that we have so far, we don't have a very good understanding about what error is according to Rouge, and that it seems that according to this metric that humans are pretty bad at summarizing. And that is even compared to what we have seen, which is not very good quality output of these systems. And then finally, as this paper that I had pointed to at the start of the presentation didn't observe, but showed all the same. And to this day, unsupervised learning is optimal for automatic summarization. Now, let's have an updated understanding of automatic summarization according to Rouge. So we started out with some notion of what a summary was. There was some algorithm development, but then we missed this metric for testing. How well were these summarization systems doing? They came up, so scientists came up with the Rouge metric, which was, great because we had nothing. But unfortunately, this has gone on to sort of redefine what automatic summarization is. Well, it's just trying to find a lot of words, a bunch of words that you think are important. And then this loop continues. And in my opinion, it continues in the wrong way because we have insufficient data, that our problem wasn't specific enough to start out with, and that the evaluation metric that we have right now is not a very good match for a more specific definition of summarization. Currently, if we're just looking at content here, we have defined the summary as the most important information of the document expressed in fluent English and within a word budget. Well, information we have approximated with n-grams. Most important, and these are just the heaviest weighted n-grams So fluent has come to mean grammatical, and because it's very difficult to be grammatical when you're just getting a machine to string words together, well, we just make sure that we take whole sentences instead, and that's what the state-of-the-art systems actually do right now. But because we're just stringing a whole bunch of sentences together, we have thrown coherence out of the window. So really, we're talking about an extractive summary setup, an extractive summary definition that we continue to use because of this metric, right? So here is really the definition that we have ended up with in our NLP community today, which is we are looking for the heaviest weighted n-grams of the document expressed in grammatical language, so extract those sentences, and within keywords. In summary, so questions that I'm looking into today is, and other people have also been looking into, of course, can we capture meaning beyond word overlap? Can we come up with a definition of summarization that includes more than just important words and important pairs of words? Now, since unsupervised summarization systems continue to be state-of-the-art, well, should summarization even be supervised? And what about summarization, the task itself, lends itself to being supervised? What indicates that it should be this way? Is summarization a single task, or does outputting a nice summary involve other things, a pipeline? And shall we not at some point start to address the concern of coherence and language fluency? And that's my talk, and thank you for listening.
Thank you very much, Natalie, for that great talk. So we have some questions that have been posted on the Q&A board. So we'll try to go through all of them, and if not, the questions will still be there, so Natalie can also answer them offline. But we'll hopefully be able to get through all of them in person, in quote-unquote person. So the first question that I wanted to bring to you is that when you were mentioning at the beginning about summarization for legal documents, the expectations for these types of documents might be very, very different from something, for instance, like a news article, or even, for instance, a book, like summarize a book, where the possible consequences of a poor summarization can be drastically different. So the question is, are people looking into different metrics or different scores to evaluate under these under these different scenarios? And as a follow-up to that, does the research community keep these things in mind when they're developing and introducing these new methods? So for what types of applications would they be most applicable or most appropriate?
So that's actually a really interesting question. I've never come across anyone who is talking about exploring like the risk of a summarization and evaluation techniques that correspond to like what is the riskiest thing to miss out on. That's actually a really interesting way to move forward. At least it gives something to hang on to, because a summarization is so elusive. But in general, in the field, I think that people don't make differences between the different domains, and that it's only when you start to talk about like supervised summarization that people expect things to move differently, the models to be different because of the different training sets. But apart from that, summarization is always talked about in the exact same way.
That's interesting, because just as a quick follow-up, the bias in data also might vary quite a lot. And so if you're using these supervised methods with biased data, then you'll still end up with biased data. So another question is more on personalization. So for instance, if you're using some of these summarization techniques for instance, extracting the important drug prospectus for some new diabetes drug, the important parts for a very young person might be very different than for somebody that's quite a bit older. So is there work in this type of personalized summarization where it tries to infer what's most salient or relevant for the user?
Yeah, so there is like a different task set up that's, called sort of query-based summarization. It might be along that stance, so people are interested. It also happens like in the news domain, people are actually interested in different pieces of information, so it's supposed to be a little bit more personalized. But what does that actually mean in practice for NLP is, that we do this first filtering stage based on the query and try to make a lot of matches on parts of the original document based on the query. So I feel like that's not super advanced, but it's actually a great idea again, especially when we go into looking at like, some things can be riskier than others depending on the perspective and the domain. So I guess in the medical domain, it would be quite important. Yeah.
Great. And we're a little bit over time, but we'll use a little bit of the lunch slack for one last question. So the question is, you were talking about Rouge, and in the table you presented, it seemed like greedy was the best when you're measuring with Rouge. Are there other approximate methods for maximizing Rouge that are better than just pure greedy?
Okay, yeah, okay, this is such a loaded question. So the answer is no, because I'm going to be a theoretician and just be like, okay, listen, the Rouge metric right now is showing that the greedy is better than the exact, even though we know that this is a hard problem. So something's going wrong. So it looks like, right now, according to the data, it looks like greedy and exact are kind of the same thing, and greedy is sort of like the lowest you can go. Now, like, this is computationally, it shouldn't be the case. There should be a lot of stuff in between. And then if you look in the literature for like automatic summarization, I mean, there's a lot of improvements over greedy, and I'm just trying to make like some sensational case that greedy and exact are too close together.
Okay, and one last question from Joshua. Shouldn't we first make progress on natural language understanding before hoping for meaningful summarization?
So I don't know. I don't think that we have to proceed in these small steps, but yeah, that would be very sensible. A very sensible thing to do would be for everyone to jump on one thing and then to jump on the other thing. But I think that we can still explore how to evaluate meaningful summarization, and we can still explore what is the actual definition of meaningful summarization without the expectation that we're going to make a ton of progress, but at least we're set up to know what this thing is.
Makes sense. All right. Well, once again, I'd like to thank you, Natalie. That was a really interesting talk. Yeah, if looking forward to having you in the panel. Everyone, just a reminder that there will be a panel right after lunch. So once again, thank you, Natalie, and looking forward to hearing you speak more in the panel.
Thank you.
Hello, everyone. Now it's time for our first spotlight session. The focus of this session will be on theoretical and core machine learning research. This session will end with messages from our sponsor, Boehringer and Microsoft. Since each spotlight is under a minute, please make sure to visit the poster session at 3 p.m. In Gallerytown to hear more about this work.
Hello, everyone. My name is Sarush. I'm a PhD candidate at Concordia University. The topic of the work that we are presenting here is on metric learning. Metric learning, due to its unique features in recording less amount of data and their capacity in handling the classification problems with dynamic number of classes, is quite popular these days. However, the existing objective functions typically impose local minimums or slow convergence rates, and they require sophisticated training mechanisms. To tackle all these problems, we are presenting MPCL here, which is a novel objective function based on cosine similarity. The most important feature about MPCL is that it pushes all of the extracted embeddings to the non-negative orthant of the feature space, and upon successful training of the network, we have embeddings that find perpendicular direction with each other. Thank you.
Task incremental continual learning, task agnostic lifelong reinforcement learning, semi-supervised class incremental learning, active continual RL. Are you confused by all of the paradigms that are studied within the continual learning umbrella? Don't you wish there was a unifying framework that would remove all of the confusion? Don't you wish there was a code base that could spawn all of those settings? Maybe that code base could let the user seamlessly switch between those settings. Maybe there could be baselines for all of those settings. Well, we gotcha. Come to the poster session for more information.
Our work on geometric directional message passing focuses on the ability to define standard directions in a graph and use them for message passing. First, we generalize message passing by introducing a background vector field on which the message is projected. This forces the message into being parallel to the specific vector field. Next, we demonstrate that we can use the gradient of the eigenvectors to find interpretable directions in the graph and use them to project the message passing. On this first example, we observe that the gradient of the eigenvector naturally yields the horizontal and vertical flows in a grid. Again, we show that these flows generalize well to non-trivial structures such as molecules. Finally, we propose different directional aggregators that can mimic both the directional smoothing and derivatives, which bridges the gap between convolutional networks and graph networks. Early results show significant improvement over the state of the art with half the error of standard methods.
Our method, risk extrapolation, or REX, is heavily inspired by invariant risk minimization, or IRM, by Arjovsky et al. From about a year ago. So both of these methods do causal discovery using deep learning. And what that means is that we have a prediction task where we don't know which of the inputs are causes of the target and which are not. And so both REX and IRM are able to uncover which inputs are in fact causes and learn to make a prediction based only on the causes. That means if you encounter a new domain where X has been intervened on, but the mechanism for Y, that is the way in which parts of X cause Y, has been preserved, the prediction rule you learned will still apply and will still make good predictions. So this is different than typical approaches to out-of-domain generalization, where you frequently assume that P of Y given X is preserved, as opposed to here we're assuming that the mechanism for Y is what's being preserved. So we also show that REX has some advantage over IRM in that it cares about covariate shift and tries to be robust to changes in the distribution of the causes of Y. On the other hand, that can also be a disadvantage when different inputs are easier or harder to predict.
Deep learning projects that use the Fisher information matrix often go something like 1. I want to do this, such as optimization for supervised learning, optimization for RL, learning theory, Bayesian deep learning, or continual learning. But 2, for actual deep networks, the Fisher information matrix is too big to hold in memory, and most linear algebra operations are too computationally demanding. So 3, I will approximate it using a block diagonal matrix, or K-fac, EK-fac, or a lower rank approximate, and so on. The goal of NN geometry is to replace the third part by making it easy to use all these representations. In this simple example, we compute the regularizer term for EWC with a block diagonal representation, then we switch to K-fac by only changing a line of code. In addition to that, NN geometry is also able to compute finite neural tangent kernels.
talk about variance-reduced gradients for graph embedding. Our work is in that accelerating the optimization of node embedding by variance reduction techniques. Generally, node embedding is a task to learn low-dimensional representations for each node in a graph by maximizing a reconstructive objective. And in S3VRG, we conduct two steps. In the first step, we estimate the expectation of gradient y based on a parameter checkpoint. And in the second step, we compute the variance-reduced gradient using this formula with only row-wise computation between x and y so that we can maintain a sparse form of the gradient. And our empirical results show a faster convergence to a better solution in most of the real data sets. Thank you.
In this project, we explore generalization in deep networks and highlight an implicit bias towards good solutions due to the dynamics of the neural tangent kernel during training. It goes like this. First, we study linear models and explore Rademacher complexity measures based on L2 balls, and show that when the kernel is anisotropic, then these complexity measures can be greatly improved. Second, we experimentally show that during training of a neural network, such anisotropy of the tangent kernel occurs. In fact, the tangent kernel aligns to the task. This in turn favors learning good solutions. Third, in the nonlinear case, we introduce a heuristic Rademacher complexity measure for learning flows and empirically evaluate it.
We will focus on setting where we have up to petabits of data such that we need distributed training, and the number of training iterations is also very large. Each worker puts a replica of the parameters from the parameter server, and this computes the gradients with the pulled parameter and then push them back to the parameter server. From the perspective of the parameter server, the stiffness of each worker is defined as the timestamp difference between the push and pull. So we show that stiffness scales linearly with the number of walkers, and also directly discounting the learning rate by stiffness slows down training by a large margin. So we propose to first normalize the stiffness and then discount. Also, with too many training iterations, the cumulative gradients would also affect the update, so we decay over every period instead of iterations. Our initial experiments show that the techniques are promising on large-scale data and clusters.
My name is Natarshan Rajkumar, and I'm presenting our paper, In Search of Robust Measures of Generalization. So we seek a theory that explains the generalization of neural networks. These theories can be realized concretely via measures that bound the generalization error, dependent on the model architecture, dataset, and other properties of the training process. Recent studies have evaluated how these measures correlate on average over populations of learning settings. We want to go beyond this and see how robust these measures really are. So a measure should be robust in the sense that it is predictive of generalization across a range of architectures and learning settings, including changes to the dataset. So a measure that works well, except for wider models, as shown here, wouldn't be considered robust. We seek a measure like this that does well in all settings. Our main contribution is an empirical framework for evaluating the robustness of generalization theories and their measures. Our hope is for this to be used in developing better theories of generalization. Our main finding is that of the 23 measures we evaluated, none are robust under the learning settings we tested them in. Check out our poster if you're interested in finding out more. Thanks for your time.
Hi, my name is Gaël Letarte and I am a PhD student at Laval University. This poster presents our paper published at NeurIPS 2019, Dichotomize and Generalize Pack-Bayesian Binary Activated Deep Neural Network. In this work, we analyze deep neural network with binary activation using the Pack-Bayesian theory, which provides pack generalization guarantees on Bayesian-like predictors. We develop a framework to train such networks, and we obtain non-vacuous generalization bounds for our approach. The origins come from the work of Germain et al. Applying pack-based to linear classifiers defined as binary predictor. The key concept is that by putting a Gaussian distribution on this binary predictor and taking the expectation, it gives us an expression in terms of the Earth function, which is easy to compute. In our paper, we apply the same idea, but for networks where the Earth function acts as an activation function. We present in details the steps for a single hidden layer network with an insightful visualization. Then we explore a stochastic approximation using Monte Carlo sampling and also how to go deeper with multiple hidden layers. Finally, experimental results show that our approach has competitive accuracy while providing non-vacuous generalization bounds. Thank you.
Hello, my name is Namyeon Kwon. I'm visiting research scientist from Samsung Electronics at SAIL Montreal. This work aims to discover useful information that can help fusion learning and propose how to apply the information to model learning. We propose an optimized step size and online adversarial data augmentation using the information. We use a deep ensemble method to estimate uncertainty of the model. We convert the uncertainty to optimize step size for new tasks. Also, we propose adversarial example generation by input gradient uncertainty. We experiment in a cross-domain scenario to evaluate more realistic and difficult problems. We train the few-shot classification model on the mini-ImageNet domain and evaluate the trained model on 3 different domains, which is flower, Caltech birds, and traffic signs. Our method shows better performance than SGD and ADAM on one-shot 5-way classification. The proposed method using a trained model with one-shot shows better performance than ADAM using a trained model with 5-shot. In the evaluation study result, performance is improved when each technique is applied. Thank you for listening to my presentation.
Hello. Today, I'm going to introduce optimizing ANN architecture using mixed integer programming. And in that work, we are motivated by the existence of efficient subnetworks that are having faster inference and achieving marginal loss in terms of accuracy when you compare it to the original overparameterized ANN. For that purpose, we are introducing a neuron importance score to our MIP formulation in order to compute the importance of each neuron in convolutional and fully connected layers. And using that importance score, we can identify and prune non-critical neurons that are having a score below certain thresholds, generating a subnetwork that can generalize across different data sets. And in order to scale our work, we are using decoupled greedy learning to represent and formulate each layer independently using a set of auxiliary networks. And thank you.
Hi, I'm Arman from University Laval, and I'm happy to present our paper Associative Alignment for Few-Shot Image Classification. We leverage recent work which has demonstrated that transfer learning can be effective for few-shot classification. Given the base categories in the pre-training stage, the feature extractor is trained using a metric learning criteria. The fine-tuning stage is tricky because any changes in the feature extractor can lead to overfitting. One possible solution is to fix the feature extractor, but this makes the classification harder. In this work, we propose the idea of associative alignment. First, we detect the base categories which are related to the novel ones. Then, we fine-tune the network using one of our proposed alignment criteria. Our approach in orange significantly improves over the state-of-the-art shown in blue in 5-shot using the ResNet backbone, object recognition on mini-ImageNet, tiered ImageNet, and cross-domain adaptation from mini-ImageNet to CUB.
Sequential information occurs in many applications. One way to model it is using recurrent neural networks. RNNs learn well, but they are hard to interpret for humans. Automata are easy to interpret, but they are hard to learn from data. Recent work shows it is possible to train an RNN, then extract an automaton that behaves very closely to it, and it can still have good performance. But can we measure how similar they are? This is the question we are trying to answer. First, we need a way to measure the difference between automata. We look at the immediate difference between the initial states, and then at the differences that arise as we travel different paths in each automaton. Next, we replace one of the automata with a black box. Now, we cannot look inside the black box, so we have to give it inputs and estimate the distance using the outputs. Once we have an estimate of the distance, we could use it to get guarantees about how much performance would be lost if we replace the black box with the automaton.
Hi everyone, my name is Utku. Today I will talk about the abstract of our recent work with Yanni, Jim, and Jan
how different are lottery tickets and the prune solutions. More specifically, I will share our results that indicate a strong tie between lottery tickets and the pruning solutions. First, we observe that lottery tickets are close to the pruning solution at the beginning of the training. The average distance at initialization are given in the table here and also visualized through MDS embeddings. Second, we show that lottery tickets go back to the same basin when trained as the original prune solution they are derived from. These results are shown here on the right side, where we observe a flat path between lottery solutions and pruning solutions. Finally, we conclude our investigation by measuring the functional similarity between lottery ticket solutions and the pruning solutions. Indeed, they are extremely similar, and as a result, their ensemble doesn't improve over single solution.
Hello everyone. Today I am going to talk about minimax theorems for games played with neural networks. The main motivation of these works is the many recent successes to solve games using neural networks. In this work, we would like to answer the question, what does it mean to solve a game with neural nets? We will focus on zero-sum two-player games, where the payoff function depends on two parameters, one for each player. Because of the neural net's parameterization, the payoff is non-concave, non-convex. One example of such a payoff is the payoff of GANs. We would like to know if we can switch min and max because it's a necessary and sufficient condition to get an equilibrium. Unfortunately, this is not true in general, but in this work, we make a key additional assumption, which is roughly that the payoff is convex-concave with respect to the neural networks themselves. In that case, we are able to prove an approximate limited capacity min-max theorems. For more details, you can come to our poster.
In this short video, I'm going to introduce differentiable causal discovery from interventional data. First, a causal graphical model is a distribution which factorizes according to a directed acyclic graph, a DAG. An intervention is defined to be a localized change in the distribution. If you do x1, its conditional is replaced by a new one in the factorization. Causal discovery is about learning a causal graph from data, in our case resulting from various interventions. The motivation is to use the causal graph to predict the effect of unseen interventions. We propose an algorithm called differentiable causal discovery with interventions, or DCDI. This is a causal discovery algorithm based on neural networks and continuous constraint optimization. It can leverage various types of interventions, including with unknown targets, and support expressive density estimators, such as normalizing flows. We show that maximizing our objective will recover the ground truth graph under specific conditions and provide empirical comparison to state-of-the-art approaches. Come to our poster to learn more.
Hi everyone, I'm Sharan and I'm happy to present our work to each optimizer a norm, to each norm its generalization. In this paper, we study the implicit regularization of optimizers when training over-parameterized models. So for instance, for over-parameterized linear regression, amongst the infinitely many solutions, what are the type of solutions to which a particular optimizer converges to? So we show that for linear models, every optimizer converges to a solution that minimizes a certain quadratic norm. And each such norm has its own generalization properties. Under certain conditions, we can show that for linear regression, it is the L2 norm that generalizes the best, whereas for linear classification, it is a norm induced by the data that has the best generalization properties. We can use this fact to move in this infinite space of solutions. So for instance, we can recover the minimum L2 norm solution by just projecting onto the data span. This technique helps us to improve the generalization performance of optimizers that typically would have had bad generalization.
Machine learning algorithms are typically compared using a single performance measure. But this measure is not deterministic. There is inherent noise. With such comparison, conclusions can vary wildly from one experiment to another. The source of noise most often considered is the initializations of the weights in neural networks. But there's many more sources, such as the noise coming from the data sampling, data order, dropout, or even hyperparameter optimization. We have observed that weights initialization is far from being the most important source of noise in many diverse tasks. To provide more robust comparisons, we propose a simulation method to cheaply measure variance encompassing all these sources of noise. As an example, we used our simulation method to verify a common belief. For each task, we selected the best and worst initializations in a pool of 200 and then trained again, but this time varying all other sources of noise. We could assume that the resulting distributions would be far from each other, but they're actually indiscernible. Please come see our poster to learn more about our method and results.
Welcome to our poster, Average Case Acceleration through Spectral Density Estimation. The traditional approach to analyzing the complexity of optimization algorithms is a worst-case analysis. This analysis gives a bound on the complexity of the algorithm, no matter how unlikely the inputs are. However, hard-to-solve inputs might never occur in practice, and so this complexity can be much worse than the observed runtime in practice. A different, more representative analysis is instead given by their average case complexity. This is the complexity of an algorithm, but average over all inputs, and is by construction representative of the typical or expected complexity. The contribution of this paper is to derive an average case analysis of optimization algorithms on a family of quadratic objectives, and to also derive algorithms that are optimal under this new average case analysis. For more details, please pass by the poster session or check out our paper.
Our work on principal neighborhood aggregation focuses on the capacity of graph neural networks to understand specific node neighborhoods. First, we generalize the aggregation framework and show that a single aggregator is not sufficient to clearly understand neighborhoods. Instead, we use aggregators concurrently, such as min and max. Then we generalize the injectivity proof of the sum aggregation and show that a logarithm scaling to the degree is more stable to larger and denser graphs. Finally, we present our PNA architecture, which combines a total of 4 aggregators and 3-degree scalars. We demonstrate that PNA outperforms the state-of-the-art by an order of magnitude on graph property prediction. We also show that PNA almost halves the error from other models on a molecular regression dataset.
Wide-angle images are more and more used for scene understanding. However, the distortion induced by short focals make it hard to apply regular deep learning algorithm on them. In this work, we studied 3 wide-angle lenses, 1 Fisher linear, and 2 panomorph lenses provided by Immervision. They control nonlinear distortion to obtain augmented resolution on the center of the image for the first lens and on the edges for the second. We trained an identical network to estimate depth from a single image and observed that the accuracy was better on the center for the network trained with the centered augmented resolution, and same thing on the edges without decreasing too much the accuracy on the other areas. To add realism, we consider lens manufacturing, creating a tolerance dataset where we introduce variation in the distortion function. We observe that the tolerance network performs better on toleranced images than the regular network. However, this experiment was still realized using simulated images with limited resolution. In the future, we want to conduct this experiment on real images.
Hi, my name is Ariella, and I will introduce our work, Latent Variable Modeling with Hyperbolic Normalizing Flows. Our work focuses on the problem of embedding hierarchies in hyperbolic space with zero distortion. This is not possible in Euclidean space. Our first contribution is tangent coupling, which is based on the real MVP normalizing flow. All operations in this tangent coupling are done in the space tangent to the origin, which is a Euclidean space. Our second contribution is a more powerful WHC, which predicts the point to which the model should parallel transport to on the hyperboloid. Here are some results of density estimation, where the top row is the target. And here are some additional results on a tree generation task, which qualitatively shows the benefits of our normalizing flows. Please come check out our post.
Hi, in this work, we propose a framework that unifies losses used in deep metric learning, in which the goal is to learn an embedding function that maps high-dimensional data to lower-dimensional points while preserving the semantic similarity between points. The vast majority of approaches used in deep metric learning rely on pairwise losses that try to directly shape the distances between pairs of points. One of our contributions is to show that most popular losses share a very similar structure and can be broken down into 2 terms. The first term minimizes the conditional entropy of the features given the labels, which encourages points from the same class to form tight clusters. The second term maximizes the entropy of features, which encourages points to spread as much as possible. On the other hand, we show that the cross-entropy loss, which has been largely overlooked by the metric learning community, can be related to the minimization of the conditional entropy of the labels given the features. All in all, our findings indicate that the pairwise losses and cross-entropy have more in common than expected, as they both implicitly maximize two views of the same underlying material information. We also show that minimizing the cross-entropy results in minimizing an underlying pairwise loss. Therefore, we argue that the difference of performances observed between the different methods mainly comes from the optimization process, and we show that the simple cross-entropy, when fairly tuned, achieves state-of-the-art results.
Trying to assess whether a system and a model display the same behavior is an important problem that has been widely addressed. The corresponding concept is called bisimulation. Since the initial works by Park and Milner, bisimulation has been studied for non-deterministic and for probabilistic processes. However, such processes are step-based. Every unit of time, a transition happens and the process jumps from its initial position to a new one. While this works for discrete time systems, an increasing number of applications deal with continuous time, robotics or physical systems, for instance. How can we generalize bisimulation to those continuous time systems? Our work shows that it is necessary to consider full trajectories instead of only talking about steps of arbitrary time. Depending on how trajectories are taken into account, we get different notions of behavioral equivalence.
Hi, I'm Amarto from UC Riverside and Mila. Today I'm going to talk about our ongoing work on game optimization. So a common issue encountered during the optimization of min-max objectives, such as GANs, is the problem of rotational dynamics, which hurt convergence. So these kind of rotational dynamics occur because each agent in this two-objective setting is ignorant of the movement of the other agent. So while current methods or existing methods for these problems employ hand-designed optimization schemes to control these dynamics, we take a more holistic approach by mapping this min-max setting problem to a physical system, so as to derive an efficient and natural, or rather physical, algorithm. Our resultant algorithm, as is currently shown on the screen, is found to improve convergence in this particular setting. And this is reflected by an improved performance on GAN training over baseline methods. For more details, please visit the link on your screen, and thank you for checking out our video.
Hi everyone, there's a slight change in our schedule, so we will proceed to our second spotlight session, and we will have the next keynote right after. This session will focus on reinforcement learning, unsupervised learning, ethic and bias in AI, and will be followed by message from our sponsor Huawei and Imagia. Once again, each spotlight is under a minute, so please visit the spotlight session at 3 p.m. in Gathertown to hear more about those works. Thank you.
Hi, I'm Charline Leland, and today I'm presenting our work on metrics and continuity in reinforcement learning in collaboration with Marc Belmar and Pablo Samuel Castro at Google Brain. Our work is motivated by several RL algorithms on continuous state spaces that assume the continuity of a set of functions with respect to a given metric. It can, for instance, be continuity of the reward or transition functions, or continuity of the value function for a set of policies that can be encountered by algorithms. Our paper studies the relationship between behavioral metrics and these continuity properties that they induce on these functions of interest in RL. We introduce new metrics and present an empirical evaluation that support a taxonomy of metrics and show the importance of the choice of a neighborhood in RL algorithms. Thanks for listening and have a good day.
Hi there, thanks for coming to our talk. In this work, we introduce SPR, a representation learning algorithm designed to improve the data efficiency of model-free reinforcement learning agents. We achieved strong state-of-the-art results on the Atari 100,000-step benchmark, both with and without data augmentation. With augmentation, compared to previous bests, we improved median performance by 55%, mean performance by 59%, and more than triple the number of tasks with superhuman performance. So how does SPR work? We augment a standard deep Q network with a temporal self-prediction objective. We force the DQN to predict its own representations of future states using a learned latent space transition model and a cosine similarity maximization loss. In doing so, we force the DQN to improve its representations of its current observations to make them more predictive of the future. Optionally, we find that drawing target representations from an exponential moving average version of the DQN can stabilize training, much like target networks stabilize deep reinforcement learning. Thanks for listening.
We note that there exists a discrepancy between the policy evaluation algorithms in actor-critic architectures and the tabular policy evaluation setting implied in the policy gradient theorem. So in this work, we will address this issue and show that it's possible to obtain policy gradient methods which are consistent with the choice of policy evaluation algorithms. This observation allows us to differentiate through a policy evaluation algorithm to obtain the gradient of the performance measure in policy gradients. The generalized policy gradient is derived using implicit function theorem so that we can measure the effect of the change of the policy parameters on value function parameters under the same policy.
Modern emergent communication is the study of how initially non-communicating agents can learn a communication protocol using deep RL. Recent work has had two overarching goals: understanding what language emerges between deep RL agents and learning a good language or protocol to build better agents. Despite the variety of goals, recent work uses two common assumptions in the setup: independent agents and discrete communication. Communication with discrete tokens can help with compositionality and generalization to human languages, but it isn't necessary for other types of generalization. Similarly, training with independent agents is useful for generalizing to new agents who won't follow a global protocol or provide internal access. This is also generalization aimed distinctly at humans. Together, these assumptions encode a worthy research goal of communicating with humans. But if practitioners have different research goals, they should be wary about which assumptions they make in their setup.
Hi. So in this work, we measure interference, which is the inner product of two gradients, and you can think about it as some kind of gradient alignment or the influence that doing an update at one point has on another point. We find that on supervised and kind of RL supervised tasks with real data, there is a weird relationship change between interference and the generalization gap. On our RL problems, we find that information propagation happens poorly with T0, but can be improved with TD lambda. As lambda increases, we get closer to the supervised target. We also find that information propagation is worse when doing policy evaluation than control, even though control is presumably less stationary. We also look at the geometry of linear region in deep neural networks, and we find that on the same data, when using TD0 instead of a supervised objective, the structure of those linear regions change in the sense that TD0 induces a heavier tail of large regions. So we point out all these discrepancies using TD0 and kind of conclude that there is still work that needs to be done before we can fully utilize the capabilities of DNNs with TD.
Hello everyone, my name is Mathieu Godbout and I'm here to present you our work named Lin Bandit Sum, reframing extractive summarization as a linear bandit. So first of all, what is extractive summarization? Well, extractive summarization is the task of generating summaries by selecting sentences from an input document. Previous papers have already explored the contextual bandit formulation and found that it is a very efficient approach to extractive summarization, where they reached state-of-the-art results with very impressive sample efficiency. We aim to go further than those papers by exploring the underlying tree structure of the extractive summarization, as can be seen on the left figure. To do so, we implement the leaf-lin UCT algorithm, which is a linear bandit algorithm. We hope to leverage the distance between sentence embeddings for an even greater sample efficiency. So you are welcome to come meet me at the poster session for more details on our implementation and our results. Bye-bye.
Hello, I am Maxime Thibault. I am a pharmacist at CHU Sainte-Justine. This work was done in collaboration with Pierre Snell and Audrey Durand from Université Laval and Mila. In North American hospitals, pharmacists review the active medications for their patients, what we call pharmacological profiles, to plan interventions. However, in practice, problems are rare. There is an opportunity to devise an unsupervised triage system that would be able to filter out profiles without issues to optimize pharmacists' time. We used a dataset of close to 3 million medication orders from CHU Sainte-Justine and trained an adaptation of an adversarial autoencoder developed for anomaly detection called Ganomaly. We observed that encoder loss values seem to correspond to the probability of finding something atypical with good correlation to the patient population complexity. A prospective study is underway to evaluate the model in comparison with pharmacist opinion. Thank you.
Hi everyone, my name is Sacha Morin. Today I'll be discussing geometry regularized autoencoders, GRI for short. So this work is about nonlinear dimensionality reduction. Specifically, we'll be addressing the fact that autoencoders typically do not preserve the global intrinsic geometry of the data, as we can see in this example here where we embed rotations of 3 different images. So in short, we leverage manifold learning to introduce better geometry in the autoencoder latent space, and we achieve this by adding to the reconstruction loss a geometric loss, which is the sum of squared distances between points in the bottleneck of the autoencoder and points in a reference manifold learning embedding, which is computed with the FATE algorithm in our case. So results are in the poster, but the most interesting finding here is that our approach actually improves test reconstruction quality, which shows that preserving geometry can serve other machine learning objectives. So that's it for me. Thanks for watching, and I hope you'll enjoy the rest of the symposium.
Hello everyone, thanks for stopping by to visit our paper at this year's Montréal A.I Symposium. I'm Laira Rafi and I'm presenting our work, Anomaly Detection based on Generative Adversarial Network. So here is the poster of our work with the proposed model, experimental result and everything. So briefly explain, the model is an unsupervised model based on generative adversarial network and autoencoder, which is a modification over the previous work with a new anomaly score function in order to detect the anomalous sample with less amount of time and, as you can see, better performance. So I will be here during the presentation. If you have any question, please reach out, and thank you.
We present a framework for the estimation of information leakage in the black box setting via machine learning. We exploit the notion of G-vulnerability, a powerful and flexible definition of leakage which uses a gain function G to model the adversary. We introduced two preprocessing techniques, reducing the problem to the Bayesian vulnerability estimation. We study the G-vulnerability learning problem, and we provide distribution-free bounds on the accuracy of the estimation. We run experiments evaluating the estimation performances in multiple scenarios and in terms of total error and standard deviation. For further details, check out the material we made available to the public.
Deep learning methods are popular machine learning models that gain widespread deployment in different domains, but there are many cases of discrimination of such models that has been reported recently, which motivates us to working on enforcing fairness in neural networks. We chose a definition of fairness which is individual fairness definition called causal discrimination, which says if two people are similar, they should receive a similar decision. We propose a component which is verification component in this work that can search through all possible inputs of a trained model to see if it's satisfying this definition or not, and if it's not, it can actually return a counterexample. Using the counterexample, we propose an approach to train a neural network which is fair without paying extra cost of performance. We also propose another approach that using this component of verification can enforce fairness during inference if we are not able to pay the cost of retraining the model.
My name is Deepak Sharma, and I'm presenting Deep Interpretability for GWAS. A GWAS aims to identify genetic variants associated with biological traits, including diseases like diabetes. In GWAS, linear models are trained marginally on individual variants. Deep models allow for joint modeling of variants and may capture genetic interactions, but association testing is often computationally intensive, requiring the training of 2 models per SNP. In this work, we use DeepLift to score SNPs according to how much they push the output from a baseline to the observed target. We train models to predict diabetes and HbA1c and use DeepLift to score features of the validation samples. We compare these scores against conventional GWAS results. This is presented for diabetes on the left and HbA1c on the right. There is clear overlap between the main peaks, with potentially novel peaks in the diabetes DeepLift plot. In the future, we aim to validate the new peaks, address confounding during training, and the class imbalance of the diabetes dataset. We also aim to test our methodology in a multitask prediction setting. Thank you for your time.
Predicting disease risks by genetic risk scores has become possible and effectiveness in the past decade thanks to numerous advances in human genetics, statistics, and data science. However, till this end, most of the related work that has been done was based on European populations. The use of these genetic risk scores may exacerbate healthcare disparities between different ethnic groups, because genetic risk scores developed based on European populations cannot predict disease risks in non-European populations. Such a reduction in prediction effectiveness is likely due to population-specific effects of genetic variants. So we're in a deadlock. The non-European study cohorts are usually small, although they provide accurate estimates of population-specific effects, whereas European study cohorts can be very large but yield biased estimates for non-European populations. We can't help wondering, can we combine these two sources to develop better genetic risk scores for those underrepresented ethnic groups? Welcome to our poster, where we found the implementation of transfer learning may give us a hand. Thank you.
Hello, my name is Xiaowei, and I recently started my PhD in electrical and computer engineering at the RACE Lab under the supervision of Dr. Ajahn Moon at McGill University. Over the past few years, many AI ethics principles have been developed. However, research on how we can measure an AI system's adherence to these principles is sparse. In this work, we want to identify the existing methods for evaluating the adherence of an AI system to the 11 most common AI ethics principles. To do this, I'm conducting a scoping review of academic and grade literature, and from this score list, I'm conducting a thematic analysis of the most relevant 200 documents. So far, I have found that a range of attempts have been made to evaluate the adherence to the principles of transparency, fairness, trust, and beneficence. However, minimal attention has been paid to the principles of solidarity, sustainability, and dignity. I would appreciate your feedback on this work and would love to hear from you. Thank you.
A typical kidney exchange program consists of a graph, where nodes represent incompatible pairs of donors and patients, and an arc represents compatibility between the source's donor and the target's patient. In this article, we explore fairness in the context of kidney exchange programs. We do so through enumeration of optimal solutions with respect to the social optimum. We employ both mixed integer programming and constraint programming techniques. Typically, the concept of fairness in kidney exchange programs is restricted to the realm of group fairness. One example is to include a certain percentage of hard-to-match patients in a solution. This article rather takes the approach of maximizing individual fairness defined according to 3 different measures. To do so, we find the distribution over the enumerated solutions that maximizes our fairness measures.
Welcome to Greenlighting ML, Confidentiality, Integrity, and Availability of Machine Learning Systems in Deployment. My name is Eric Galinkin. I'm one of the authors of this paper with my co-author Abhishek Gupta. Our motivation for this project is that there's a lot of interest in building systems that protect data of users and adhere to ethical principles. And in data protection, there's a very natural synergy between security and ethical practices. Current systems for ensuring ethical practices work well conceptually, but are onerous to put into practice. They typically involve a lot of manual reporting and recording of data. So our idea is to integrate these things deeply into our workflow to detect vulnerability to adversarial examples, which risks potential user data and misclassification, and integrate this via continuous integration and continuous delivery support. Thank you.
Hello. In the early days of the pandemic, I wondered how machine learning could help to reduce the spread of the virus, using information that users could provide on their phone. And I realized that the decisions of traditional digital contact tracing were binary. They only used the positive or negative result from tests, in a form of bang-bang control. Instead, using this extra information from users could provide an early warning signal to them and their contacts who do not even yet have symptoms. The next question that came up was, how can we do this in a way that preserves privacy and dignity of users as much as possible? The answers came through this project, probably the one I worked on the most intensely in my life, for which we built the most detailed agent-based simulator of the spread of the virus using the available medical data. That allowed us to indeed validate these ideas and how machine learning could help to lead a reduced spread of the virus while not centralizing any information about people's contacts and movements.
Symbols is a synthetic dataset generator designed at Element AI. The main objective is to provide a tool for probing the behavior of learning algorithms. For example, by changing the distribution of the latent factor, one can perform a counterfactual analysis about the learning properties of a chosen algorithm. To build the generator, we leverage the creativity available in the space of open source funds. We can render more than 12,000 different symbols across 14 languages. For rapid research iteration, we can render images in very small resolution, but when more features are needed, such as multiple symbols in the same image, we can increase the resolution. Various types of backgrounds and inclusions are also available. The rest of the paper shows the versatility of the generator by performing scientific discoveries in 6 different machine learning setups, including unsupervised learning, object counting, and fusion learning. For example, we highlight an important failure case in active learning when one uses prediction entropy as a query function. It can become far worse than random.
Hello everyone, I am Gauthier Gidel, and today I am going to talk about our latest paper, Adversarial Example Games. In this paper, we want to craft adversarial examples that are epsilon close to a given data point x in order to fool a classifier f. In order to do so, we will solve an optimization problem that consists in maximizing the classification loss of f. This is done under a threat model that consists in what we assume to have access to. Either gradient, usually this is called the white box threat model, or softmax value, which is called the black box threat model. In our work, we try to tackle a more realistic and challenging threat model, the non-interactive black box threat model. In that threat model, we want to attack a target model FT without interacting with it. Instead, we assume to have access to a model hypothesis class. In order to craft adversarial example against FT, we will optimize over the class F to get adversarial example that can attack any function in F.
Hi everyone, thank you for coming to my poster. My name is Chao Yan, PhD student at McGill University, working on machine learning with computational biology. The work I'm talking about today is a method to represent and generate complex RNA secondary structure. RNA is a type of macromolecule that can form complex structures which can influence their role in the regulatory landscape of cells. Due to the consideration of the specific dynamics of RNA folding, we designed a hierarchical encoding strategy as shown in figure 1a and b to represent the RNA on its molecular graph level as well as on its junction tree level. Our generation algorithm is also hierarchical regressive in that it interleaves three types of predictions during the process of decoding the tree topology and nucleotide branches of the molecule. Additional constraints can also be added to our decoding algorithm to ensure the validity and stability of the generated molecule. And we have some results for training unsupervised VE, which shows the performance of our task. We would also like to know that this is an ongoing work, and the full paper will talk about the different task formulation, where we train semi-supervised VEs in the context of predicting RNA-protein interaction, which helps with a goal-oriented design.
Hi everyone, we are happy to present our work on self-calibration for gesture recognition based on muscle activity. Muscle activity provides an intuitive and non-invasive interface from which to control machines. However, preserving the system's performance over multiple days is challenging, and this is due to the transient nature of the recorded signal, as when the interface is employed over several days, the user needs to recalibrate before every use. This work introduces a new domain adversarial self-calibrating algorithm named SCADAN, which adapts the weights of the network over multiple days in an unsupervised manner. SCADAN is compared and tested against various algorithms and achieves state-of-the-art performances on multiple datasets and multiple network architectures. As SCADAN has no computational overhead during inference, employing the proposed algorithm is a net benefit for long-term use of muscle activity-based gesture recognition systems. We will be happy to discuss this work in more detail at our poster session.
Hello everyone, this is Fazi Hassan. We propose two approaches to improve the transcription factor binding size prediction, one for training and one for inference. So in first approach, we regularize the model objective function such that the model prediction on the unlabeled phylogenetically related examples are as equal as possible. In the second approach, we combine the scores of a pre-trained classifier such that the phylogenetic relationship is maintained. We show that there's an improvement of 3% in the real data set. And in theory, our approaches are applicable to any sequence-based function prediction task. Thank you.
Thanks to recent advances in sequencing, we have a lot of RNA sequences for which we do not know the structure or the function. RNA 3D modules are small substructures that can help us learn more about those RNAs because they have a clear sequence signal and are important structural organizers and ligand binding centers, where ligands are small molecules like drugs. So if we want to identify them in sequences, we cannot use energy models because they are networks of non-canonical base pairs which are too unstable for us to know their energy signature. So instead, we use Bayesian networks that allow us to encode the dependence relationships between partners of the same base pair. And given an input sequence, we sample the secondary structure. And then for each loop we identify, we try to size match with our database. And if the size of the two loops can match, then we use the Bayesian network to compute a score that tells us how likely it is for the module to be there at this position.
Hi everyone, I'm Reza and happy to present our work and analysis of the adaptation speed of causal models. In this work, we consider the problem of discovering the causal process that generated the collection of datasets. We assume all the datasets were generated by unknown sparse intervention on a structural causal model G. Recently, Benji et al. Argued that among all the structural causal models, G is the fastest to adapt from one dataset to another and proposed a meta-learning criterion to identify the causal direction in a two-variable SVM. While the experiments were promising, the theoretical justification was incomplete. Our contribution is a theoretical investigation of the adaptation speed of a simple two-variable SCMs. We use convergence rate from stochastic optimization as a proxy for adaptation speed. Using this proxy, we show that the SCM with the correct causal direction is advantage for categorical and normal cause-effect dataset when the intervention is on the cause variable. When the intervention is on the effect, we show that the fast to adapt heuristic is not always valid.
Okay, I will be introducing our next speaker, Zach Lipton. He's an assistant professor of operations research and machine learning at Carnegie Mellon University. And his research spans core machine learning methods and their social impact and addresses diverse application areas, including clinical medicine, natural language processing, and the intersection of causality and deep learning. He is the founder of the Approximately Correct blog and a co-author of Dive into Deep Learning, an interactive open source book drafted entirely through Jupyter Notebooks. So we'll hear from Zach now.
Cool. Can everyone see my screen? I'll take that. Take the silence as an affirmation. Okay, great. People are saying yes in the chat. Cool. So it's great to be here today. Thanks for having me. I'm extremely grateful to the organizers who for whom I have demonstrated that video editing and video timeliness skills are anti-correlated with having a position as a computer scientist. Today's talk is going to address algorithmic fairness, and I'm going to take maybe perhaps a zoomed out or wider view on these issues that isn't maybe just focused on the algorithms and the ways that we change them, but actually on sort of their social context and the various kinds of principles, not just statistical, but also, say, for example, normative, that come into play in these kinds of decisions. And basically, to just give some wider framing, why do we care so much about algorithmic fairness? Well, there's certain classes of decisions that always have associated social and ethical concerns. Things like who should go to jail, who should have what job, who should be chosen, who should be granted a loan. There have always been fairness questions associated and debates about the ethics of how these decisions are made. What's changed is the way that these decisions have gotten made. Increasingly, they tend either to have decisions that are either made by or made with input from various statistical prediction tools. So as we start operationalizing this sort of sphere of technology that we've developed mostly for prediction to drive decisions, that change from prediction to decision suddenly now puts us in the position where we are responsible for the decisions that are getting made in these sort of ethically fraught environments. And as a result, there's sort of a blurred line now between what is a social and what is a technical concern. This is certainly not a brand new phenomenon, and there have been people discussing ethics associated with technology for many decades now, including some pioneers in our field like Helen Nissenbaum or Tarleton Gillespie who've been talking about this since kind of early computing and internet or at least early personal computing and the internet. But this sort of, at least in the machine learning community, caught a lot of national attention and sort of spurred the creation of like a veritable subfield within the machine learning community around the time of 2016, when machine learning this sort of rise of like this kind of wave of machine learning enthusiasm was sort of starting to crest. And it turned out that the focal point here wasn't actually a particularly advanced machine learning tool, but rather a simple prediction tool that was being used to guide decisions in criminal sentencing or criminal like bail decisions, various decisions in criminal justice. And so ProPublica had this article, and they analyzed a system that was being used to assign risk scores to defendants who are awaiting trial. And the thing that they ostensibly the score is supposed to communicate is how likely is somebody to reoffend if released. And the idea is that you would give a score to a judge and it would help them to make a decision about who should be released or not. And so they analyzed it, and they came to the startling conclusion that this score was biased against Black individuals. So they picked a particular metric. You know, they looked at, you know, so there's many different ways you could look at it. Some people have looked at like false positive rates, false negative rates, looked at, you know, various aspects of like the calibration of the scores when there's continuous scores coming out. Is it calibrated within each group? And so I would like to, you know, so a lot, basically a whole academic community kind of emerged to take on all these, you know, pose many different sort of plausible seeming statistical parity conditions to say, are they satisfied among white versus Black defendants, and figure out what is the right way to formalize fairness. And immediately sort of came to sort of the conclusions that some people were sure that the system was unfair. A few people dissented and said that according to their metrics, the system was actually fair. Immediately, people found out that the different metrics that they were proposing were often mutually irreconcilable. So you sort of couldn't be fair by all of them simultaneously unless you were actually starting from data where the groups were sort of identically distributed. But it sort of galvanized a whole kind of field of people looking at these issues. And what I would like to do when you look at the situation is to also step back and think of, is statistical prediction even the right framework to be able to make all the relevant determinations about what's fair? Like, I'd like to note, you know, a number of complexities that sort of were left out of a lot of the early academic discourse. One is that you don't actually even, the quantity you care about is someone commit a crime when released. You don't actually observe from much of the population, you don't even have a chance to observe whether or not they commit a crime because they're not released. Then among the released population, you don't observe whether they commit a crime. You observe whether, given that someone committed a crime, or whether someone committed a crime and was arrested for it. And that is obviously determined not just by differences in who commits a crime, but also differences in how people are policed. Other things that were left out is people focused a lot on the properties of statistical predictor, but didn't think about what are even valid inputs to the predictor. These are questions that emerge in sort of the relevant moral and political philosophy as concerns about procedural justice. And there have been almost no discussion about the procedural justice of these systems. Can you even take certain information into account? And can you make a decision about whether or not to incarcerate someone on the basis of a fact that's completely outside of their control, like what is their occupation or how many siblings do they have? So there's sort of a rush to deploy the technology, a sudden realization that things go wrong, and then a sort of rush to propose solutions that is often kind of maybe are sometimes flawed in the ways that the original technology is, and I'll elaborate on that soon. Another kind of moment that caught a lot of national attention here was some great work by Joy Boylamwini and Timney Jibru, who looked at commercial face recognition systems and made the observation that the performance characteristics on these systems across gender and across racial or ethnic lines and the various intersectional groups were widely disparate across different groups. So this, I think, did a great job of getting people to think that, okay, immediately I know that there's some kind of differential aspect in how this technology affects whatever its effect might be, that it seems to be different for members of different kind of socially salient groups. But you know, the one kind of area where this becomes fraught is that, you know, I think maybe the bigger value is not just the point that the accuracy is different, but to get us to think about the ethics of deploying systems like commercial face recognition, right? Because if you step back, even if everyone were recognized equally accurately, not everyone is equally subject to surveillance, and the benefits and harms of commercial facial recognition technology would not necessarily be equally apportioned among society. For example, people living in public housing might be more easily surveilled, and if the consequences of being recognized by such surveillance systems were in general not good, would face, you know, sort of the brunt of the burden. So there's a lot of fraught issues that arise from the deployment of a lot of this technology. Another instance that sort of caught a lot of people's attention was people noticed that these word embeddings that people were using for all kinds of downstream natural language processing tasks, that they exhibited certain statistical disparities. So, for example, you know, you would learn something like man is the computer programmer as woman is the homemaker. So again, these models aren't trained to perform this analogical reasoning. They're just performed to sort of be accurate at predicting which words are in their neighborhood. But the resulting word embeddings have had these properties that sort of enabled, by some principle that we've attempted to explain but maybe don't fully explain, to do this kind of analogical reasoning. But when you start probing it, you find that it seems that there's strong evidence the model has kind of picked up on the kinds of biases and that we expect to exist in society and to be reflected in language. And again, here there's sort of a concern of, well, what, if anything, but what potentially are the ways that this sort of disparity as reflected in the word embeddings might influence the sort of discriminatory or not behavior of the downstream systems that are built on top of those basic primitives. So, one challenge here is that I think that people are on the right page of recognize there are serious problems. And I want to be clear when I sort of criticize some of the way that we've attempted to approach it technically. This is not to say these aren't problems. These are absolutely problems, but they challenge us to maybe go beyond our sort of normal toolkit. And I'll give an example of where people sort of gone wrong is that, we're a little bit more disciplined about how we use technical methodology or technical terminology. But when we start talking about things like fairness or ethics, there's a tendency in technical papers when the reviewer is likely not someone with a background in moral political philosophy, but someone who's got a background in Q learning, to start using these words in a kind of loose way. So we start saying the algorithm's fair, the data's fair, the data's biased, the algorithm's biased, the pre-processing is biased, the decision's biased. And there's sort of a failure to make the right categorical distinctions. What are the specific things that are concerns of fairness or justice, and what are the relevant technologies and their precise relationships to the ultimate object that is a sort of concern from a standpoint of justice. And so, justice has to do in general with the allocation of benefits and harms, and it has to do with rendering unto to each their due. In a longer version of this talk, I would go deeper into the sort of like very, very basic philosophical underpinnings. I don't have time here, but the point is to say, if there's no decision being made or nothing is being rendered onto anyone, there is no concern about fairness, right? If I just show you a set of vectors and say, are these fair? It's kind of a meaningless question. What does it mean for a vector to be fair? And even if I tell you, well, some of these vectors are associated with females and some with males, are they fair now? That's still not a well-formed question. And the reason why is I could ask a question like, is it possible to discriminate on the basis of the associated vector? Is someone more likely to be male or female? And if I'm able to do that, maybe I think there is a difference. But what I don't know is how does this difference fit into the set of like normative principles? Like how do these decisions ultimately fit into some kind of decision that's being made and the set of obligations that we have to people? And another important thing that we need to know that's not represented here is what do these vectors even mean? What is the process by which they arose? What are they measurements of? And so if you have a characterization of a problem that just says you have a vector, you have a demographic, that's often just not enough to even make a coherent statement. So we need to just take a big step back and have this kind of context-specific awareness of what are the kinds of decisions, what are the principles at play, why are there disparities in the first place, who are the socially salient groups that we must sort of be concerned about from a standpoint of distributive outcomes, and then ultimately what decisions are we making, and how do those decisions not just impact the confusion matrix of our classifier on static data, but the actual, downstream, downstream impact the lives of the people who are subject to the decisions that we're making. So in general, there's a bit of confusion where technological, philosophical, economic, and legal terminology are sort of often overloaded in confusing ways. And in this talk, I'm going to go kind of much deeper into just a specific example. I don't have time to discuss all these different corners, but I'll discuss the way that people have attempted to formalize the law in technical language and maybe gone a little bit wrong. So overall, there's a little bit of a pernicious pattern here that I described earlier, which is that people are sort of looking out into the world. Like basically, we have these statistical prediction tools that are, from a standpoint of prediction, really powerful in a way that the previous generation of tools weren't. And the tooling is there, and the awareness is there, and the receptiveness to these tools is there. So there's like a sense of opportunity. So people are looking out into the world and finding problems. And most of the problems that people find ultimately have something of the flavor of automation. They look like decision-making, not like prediction. So, we care about something like impact in a real world situation. We care about something that looks more like a causal effect. And we also maybe have some other set of concerns, like social concerns or moral concerns. These are all not really well formed within the statistical prediction framework. But what we say is, let's just fashion a surrogate prediction task for whatever our real world problem is. So we want to curate engaging playlists or whatever. Let's just focus on predicting clicks based on historical data. You want to predict, you want to determine who merits release on bail. Let's just focus on predicting who's likely to get rearrested based on the historical data condition, from the subset of people who were released in the past. So we come up with a statistical prediction problem that, it's like you have a proxy objective, it's predicting a statistical quantity, not the causal quantity you care about. Everything's kind of wrong with it. But we just sort of focus on it and lose sight of the bigger picture. We define some metrics of success, like accuracy or AUC, that are only really appropriate if we've assumed that prediction is the underlying task. And ultimately what happens is that some kind of trouble arises due to this mismatch of problem description. And then here's where, we run the risk of maybe even those of us who are meaning well of being part of the problem, is that then often some of us rush and say, to sort of solve the problem, say, here's the FAIR model, the FAIR classifier, the ethical agent. And we sort of come up with a way that really sort of purports to solve the problem while working entirely within, just another kind of myopic statistical prediction framework. So we've changed something. We've added a regularizer, we've added a constraint, but we haven't really thought about the wider set of considerations. And so we end up proposing solutions that are sort of flawed in precisely the same ways as the original solutions were, at least conceptually. That's not to say that they're not ever mitigating some of the damage. I think there are contexts in which we are. But sort of conceptually, we have a sort of a rushed attempt to sort of claim to have solved the problem. And the danger is that we can often mislead the public by purporting to have addressed the problem when we really just redefine the problem. And this is a thing that we often do in AI. We don't know how to solve reading comprehension. We know how to solve span prediction. So let's just call span prediction reading comprehension. And the criticism is always, well, if we ever solve reading comprehension, what are we going to call it? Well, can't call it reading comprehension because that's taken. So the danger of solutionism is real, and I'll show you an example. Here's a company called Pymetrics that is using machine learning to guide decisions in hiring. And so what do they have on their website? They might have taken it down since I started giving this slide in my talk, but they had this kind of like all the startups, we have bank grade encryption and something. They also say we have bias-free algorithms. And I say, we know that diversity is important, but we've got this covered. We read a paper. It said that this particular statistical condition equals fairness. And so we just blindly applied a simple heuristic that ensures that that condition is always met. And now we're claiming sort of like certifiably bias-free algorithms. The problem is that there's greater context required. In some contexts, that condition that they're trying to satisfy might correspond to, actually roughly what, reasonable people would think of as being fair. And at the same time, there are other situations where those very same people would characterize it as, being patently unfair. So it doesn't distinguish between, are you benefiting people who are historically oppressed, or are you hurting people who are perhaps overrepresented, but despite the fact that, whose success comes despite discrimination, not because of it. So here's kind of the high-level setup for how these problems are typically cast. And I'm going to be very, very kind of high level here. Is that nearly all the machine learning that gets deployed in the real world has the flavor of supervised learning. And yes, we talk about estimating causal effects, and we have kind of a deep philosophy in mathematical machinery. And yes, we talk about reinforcement learning, but most of the tools that are deployed influencing real-world decisions have the flavor of supervised learning, or even if unsupervised learning is used as often as a precursor to training some kind of classifier. And these systems, you all know how they work. We grab a collection of inputs, a collection of outputs, or targets that are sampled, hopefully independently from some distribution, or at least we assume independently. We feed them into the machine learning algorithm, and out pops a model. And the idea is if we've done our job and extracted a sort of pattern that generalizes, then with high probability, the inputs that we feed into our model will result in outputs that are in expectation close to the true targets. We happen to be making these decisions now very often with neural networks, though not always. Like the criminal recidivism predictions are not generally made with deep neural networks, but with simple linear models. And a lot of the focus in the rhetoric, I think, has been shifted to the fact that, like, well, the models are really complex and who knows what's going on or whatever. And I think that that focus actually is a little bit misguided in that I think that it misses the bigger picture, that the problem isn't really the functional form. Am I using a neural network, a big neural network, a wide neural network, a decision tree? It's really, I think, the framing of the problem is statistical prediction in the first place. I don't think it's the hypothesis class. I think it's that where a lot of what gets lost is between the real problem and its framing as a statistical prediction problem, not the modeling choices that are made along the way. Again, the fact that we're using very deep neural networks, I think, is virtually of no consequence here. I would like to notice, because I am making these points about the ways that by pretending something is a prediction problem, we lose sight of the very concerns that we care about. But I do want to just take one moment to point out that even if we had the rare problem that really is well-formed as a prediction problem, like we're doing diagnostics, the distribution of photographs of, biopsies coming in is not changing. We're not influencing what the future distribution will look like by the calls that we're making. Our only goal is to just accurately say cancer or not cancer, something like this. You can still have fairness concerns that arise even if prediction really is what we care about. For example, there's the well kind of recognized problems of if some groups are underrepresented in the data, the benefits of automation might be unequal. So for example, people who speak with a certain accent, if they're not in the data set, then they won't benefit from the same accuracy statistical predictions among them. Or if you train a system to recognize skin cancer, but you train it mostly on white skin and not black skin, you're going to have an issue. There's also still the issue that even if what you cared about was statistical prediction of some quantity, if your training labels themselves are noisy or biased, or you only have access to like a surrogate task, so like you want to just predict, will somebody, let's say you really believe it's enough to predict, will somebody be a good employee, but you don't observe will they be a good employee, you observe were they promoted, and where they promoted was determined by the particular biases and beliefs of the people who are the managers at the time. I'd also point out that for things like groups being overrepresented, equalizing representation is no assurance of equalizing performance. And that's because the task can actually be easier for one group than for another group because the quality of measurement, the quality of signal for them is better. An example of this might be like in PhD admissions or something like this, where when people come from famous schools and have famous recommenders, it's easier to determine, when you know how to read their transcript and you know how to parse their letter, it might be easier to read the signal than for someone else for whom you don't have the same quality of signal. So, and there's all kinds of complications. It's not enough to just say, I don't want my model to depend on some feature, because all of your features are correlated. So it's not quite clear what it means to not depend on a feature. If you remove the feature and you get out the same model. And again, all these measurements are often have a kind of fuzzy relationship to the underlying quantities that we care about. So I'm not going to spend too much time talking about causality, but I just want to point out that causality is, I think, relevant here in a couple ways. One is that some fairness questions, even if we can't actually learn the causal models, are more coherently framed in terms of certain causal problems, both in terms of how did a disparity arise in the first place, what do we think the impact of a decision will be, if we're auditing an algorithm, what is the mechanism by which we think a demographic trait came to be associated with the model's outputs. I think it's also important in a way that causality causes you to think in a different way than just doing sort of machine learning business as usual, which is that you have to think about questions of identifiability. You can't just go and say, I'm going to train the model and get the best model. There's always, whenever you can calculate a metric, there's always a best model in class. But causality makes you think, are the problems that I care about, is the quantity that I'm after even something that's identifiable from the data, or do I have to go out and observe something else or add on some assumption that's not there? And I think a lot of these concerns about fairness, we want to rush to the point of just assume that we have enough information to make the determination about what is fair, without thinking, do I even have the right background knowledge to understand the context of this data, to understand how that bears on how decisions should be made going forward. So I'll speak now about how people in machine learning have attempted to borrow ideas from the law and how these things get translated into sort of mathematical formulations that may or may not be, I'll just say may not be faithful to what the law intends. So a lot of the discourse here is driven by United States law, in particular the Civil Rights Act of 1964. And Title VII of the Civil Rights Act of 1964 introduced two important legal doctrines surrounding considerations of discrimination in various spheres of life. One is, the first thing they did is they defined a set of protected characteristics. These are like group level distinctions that we care about. And they included age, religion, race, gender. They didn't include some of the distinctions that are now considered to be protected. I believe there's a Supreme Court decision recently on the fact that sexual orientation is considered as protected via a lot of these protections, whereas it wasn't explicitly enumerated as a protected characteristic in 1964. These are normative considerations that have changed as society has evolved on these issues. Disparate treatment is the legal doctrine that addresses intentional discrimination. So this includes decisions explicitly based on some protected characteristic, like, they're going after, the law is usually not like mathematics, not defining a universal truth. It's going after thinking like, what is the particular problem we observe and how do we deal with it? So this is going after the people who, they think are just outright, saying, we don't want to hire people from this group. They go out and say, this is what we want to capture. This is what we want this doctrine to address. So the key detail here is that it's intentional discrimination. Now that includes intentional discrimination based explicitly on the protected characteristic, but also based on proxy variables. And in machine learning, we've sort of forgotten about this, ignored the intention part and focused on the explicit part. So often, if you see a machine learning paper talk about disparate treatment, it often just means that the resulting model is not allowed to take the demographic explicitly as an input. But that's not quite what the legal doctrine means. It concerns intent. And if you try to map this on the machine learning, you see how fraught this becomes. Whose intent? The intent of the people who made the decisions that we're training a model to imitate, the intent of the people who curated the cohort for then training a model, the intent of the people who did the pre-processing, the modeling, who deployed the system, who owned the company that ran it. It's not quite clear. Now, disparate impact is a different legal doctrine here that basically is meant to address the more complicated cases where even if someone wasn't intentionally discriminating or had a superficially neutral practice, there can nevertheless be an unjustified adverse impact on members of a protected group. So a classic example here was that there was a company called Duke Power that had some, I'm trying to remember exactly what the test, I think it was something like they would only promote people to manager if they completed some level of education. And it so happened that I think it was like in North Carolina in the 1960s, there was a huge gap among blacks and whites in terms of the fraction of people that had access to that level of education. And this wasn't really like the degree wasn't really materially necessary. Like it wasn't like you couldn't possibly be a good manager if you don't have a high school degree. So this law is meant to address this kind of setting. And what the way it goes is first the plaintiff has to demonstrate that there's some kind of actual disparity just from sort of what we observed to at least justify launching an investigation, but that's not where it ends. Then the defendant has to come back and try to argue that their decisions are justified. So you could say, okay, well, maybe there's not equal number of every group, but hey, we're running the Olympic running team and we selected people just on the basis of their running speeds. And this is, you can't do the job unless you're one of the fastest runners in the world. That's the definition of the job. And that is the criteria that we use. So they make a more procedural argument, say every consideration along the way, these are the right considerations. We sort of don't have a choice. They're justified by business necessity. And then the plaintiff can turn around and can make this kind of almost causal argument. They can make what really looks like a counterfactual argument. They have to say, well, here's a different policy that you could have employed. And they have to make an argument that it would have satisfied the business goal, but it would not have given rise to the disparity among the groups. And so that this would be a sort of better alternative practice. So you see how complicated this law is. It concerns this notion of justification. What does this mean? It concerns this kind of counterfactual idea, this kind of off-policy question of like, what would the alternative practice have given rise to? In the fair machine learning literature, these things have all been squared off in a kind of strange way. So what we've done is we've added this sensitive feature to the mix. So we say we have targets and features, but we also have the sensitive feature. And these are all going to go into the ML algorithm now. And now the output is going to be a model that satisfies, some or some combination of fairness conditions. So we want to basically, all these conditions take the form of some kind of parity. They say we want to make the groups equal in some sort of way. So we say we want the outcome to be dependent upon of the group status, so that if you condition on the group status, it tells you nothing about the outcome. We say sometimes we want something that like blindness, which is usually called disparate treatment in the ML literature, but this is not actually disparate treatment. It doesn't address intent. It just concerns the fact that you don't use the feature directly. There's ideas say, oh, you can map to a representation such that the demographic cannot be inferred. And this is entails impact parity, but it's a little bit stronger in that it also gives you impact parity for any kind of task that you address on top of those representations, with the same distribution, the same population. And people also focus a lot on different kind of quantities of the confusion, calculated based on entries of the confusion matrix. Like, do we have equalized false negative rates or false positive rates or both? So treatment parity in the ML literature is really simple. You say just don't look at the feature. So the resulting model can't look at the feature. What people have called disparate impact, or I've sort of turned these around because I want to really distinguish between what we're doing in ML and the law. I don't want to overload the terminology, so we'll call it impact parity. What they say is basically, hey, you have the sensitive feature, which it plays a role in the parity condition, and you need to create a model that satisfies this parity condition. And the resulting model may or may not use a sensitive feature. That concerns treatment parity. Impact parity is sort of agnostic to it. So now the problems here are that if the groups are already identically distributed, this is very easy. You just need to be blind, and you'll have every other kind of parity for free. If they're not distributed identically, in general, you find that all these combinations of parities are sort of tend to be mutually irreconcilable. On top of that, you have this problem that statistical parities, again, are quite divorced from the actual legal and philosophical principles that we care about here. They often don't map one-to-one these stated definitions. So it's common to hear people in ML describe these things as 21 or 49 or 72 or wherever we are now, definitions of fairness. But this is already, I think, a kind of verbal slip that is misleading people. We don't have 100 ML definitions of fairness. We have 0. What we have is 100 different parity conditions that are related in various vague ways to some corresponding fairness principles. So often the way we're forming this problem lacks even the basic ingredients to actually make the determinations about what is fair. There's a lack of an account for how disparities arose, a lack of like a normative principle for who's responsible for intervening and in what way they're able to, and a consideration of what are the available interventions, and actually like a causal analysis of what actually is the will the impact of these decisions be? And once you have a policy, do you see what the impacts are, and do you revise the policy depending upon whether it's hurting people or helping people? With my postdoc, Sina Fazalpour, who is actually in the philosophy department and working with David Danks over there and with me in ML, we made this connection between what's going on in ML and actually in a much earlier debate that happened in philosophy, which is a distinction between the ideal and the non-ideal approach. The ideal approach is this kind of naive way of saying, let's just imagine a perfect world and then go look at like what are things that we think would be true in the perfect world, and look at the real world we see and just try to go after these differences. Just if it's different from the ideal world, we should eliminate it. The problem here is that this can be used in a sort of problematic way. Like, for example, people have used this sort of a way of theorizing to argue against affirmative action. They say, in the ideal world, we'd all be colorblind. Therefore, in the present world, all decisions should be colorblind. And so the kind of criticism of it is this, what's called the non-ideal approach, is to sort of say, hey, the ideal is nice. We all want to get to an ideal. It's a nice goalpost or hypothesis, but it doesn't by itself give us practical guidance for how, given that we live in the non-ideal world, and that given that we live in a world with a history of injustice and all kinds of people who don't sort of comply with what justice demands of them, what then are our responsibilities, and what then are the actions that we should take to come closer to the ideal, which are not necessarily going to be the same exact policies that would be in place if you lived in the ideal world. One way of like bringing this to bear on the discussion of fairness is to say that, this kind of sheds some light on these impossibility theorems. To some people, these impossibility theorems are sort of taken as, people don't, know what they're talking about, as, fairness is impossible. But really, that's not what it's saying. What it's saying is that if you start in the non-ideal world and you're just one decision maker, there's no action available to you that will make you instantaneously achieve the ideal in every respect. And so this is a kind of like naive exercise, and that what you actually need is some kind of practical guidance for how the interventions that you make are going to lead you closer to or further from some ideal, and what is the thing to focus on now that actually is going to make the long-term benefit. It turns out we're not the first people to raise this criticism. So Sina unearthed this entire debate already happened and was somewhat resolved in 1994 among economists who also in their day had attempted to formalize ideas about fairness. So they had what's called the axiomatic approach, where people basically hand out a bunch of axioms about what they think fairness should look like, what's the form that equitable rule should take. And the problem is that each of these things seem independently reasonable or plausible, but when you pile them on top of each other, they inevitably lead to these impossibility theorems, which just sort of confirm the skeptic's predisposition to believe that the problem had no solution. But, again, the point here is not to say that fairness was impossible or equity was impossible, but rather that, given that you're in a particular situation that's unequitable in many ways, not all desirable conditions are instantly satisfiable, and you have to make some kind of choice. So I'll show you where things go off the rails with just finally an empirical example, is that a lot of people have sort of taken these sort of misinterpretations of what the law means, just disparate impact parity, or disparate impact meaning just you can't have the outcome disparity, and disparate treatment just meaning you're not allowed to look at the feature. And so they say, okay, you're not allowed to look at the feature, but you have to have parity on the outcomes. So we're going to design a model where the sensitive feature is not an input to the model, but the sensitive feature will be used during training to choose parameters such that outcome parity is, overall statistically achieved. And so they do this. And now where things go wrong is that it turns out that, well, if you just wanted to trade off accuracy subject to some constraint on outcome parity, actually explicitly using the sensitive feature is the optimal thing to do. It's very easy to do. You just go and set different thresholds for the two groups. And this achieves what you want. You want to have greater representation among women to correct for historical injustices. You should just be transparent about it. Hire less men, hire more women. And this is the optimal way to achieve this trade-off between utility and parity. And when the danger is if you train one of these algorithms and it turns out the features are sufficiently rich, you can infer with 100% accuracy what somebody's, say, gender was or what their demographic was based on their non-protected features, then because it's the optimal thing to do for any sufficiently powerful model, the solution you get will actually be identical to the one that uses the feature explicitly. So because it's optimal, whenever it's possible, you will actually recover it. And so the result is that, we've designed algorithms, we're telling people that they comply with the law, but actually they're doing exactly the same thing functionally as something that people are claiming doesn't comply with the law. And the added layer of complication here is that it's not even true in the first place that using the feature necessarily doesn't comply with the law. There are cases where you are allowed to use the feature, and promoting diversity rather than encouraging discrimination actually is often considered to be like a valid use of that information. Now, if it turns out you can only noisily infer the demographic feature from the non-protected traits, these disparate learning processes can result in all kinds of bizarre side effects. So I'll give an example now to end. We have a data set of about 9,000 students considered for admission to a master's program at a large US university over 11 years. Our labels are admissions decisions provided by a faculty admissions committee. And our attributes are gender as our protected trait, and then also things like country of origin, interest area, GRE score, et cetera. These are all additional features. And what we added is, just in case you don't think there was actual discrimination in the particular progressive university system that was willing to share their data with us, we flip 25% of the labels for female candidates who were accepted from positive to negative, just to simulate the situation in which there was sort of a kind of overall irrational bias on the basis of gender. So we can now look and say, what happens when you deploy one of these disparate learning process type algorithms? And there's many forms these algorithms can take. Things like fair GANs are often like this, but there's many, many more. And when you look and say, what's going on here, I'm just going to unpack this plot. This is the most important plot here, is we can look and see the standard ML thing is just predict the probability that they would have been admitted historically, and then just threshold based on that score. And you say, okay, the people above, we decide we're going to accept, people below, we decide we're going to reject. I'm not saying anyone should actually make a decision that way. So that would be like the sort of standard naive ML thing to do. Now, we can also train a model to try to predict, based on the non-sensitive covariates, how likely is the individual to be female. And so now we can look and say, what happens when we go from the standard decisions, which are just this dotted horizontal line, to using one of these disparate learning processes. And what we find is that some people have their decisions flipped from negative to positive, others from positive to negative. So here, all the yellow people are male, all the blue people are female. Arrows up mean decision flip to positive, arrow down means decision flip to negative. The right panel is just to zoom in on the critical region. And so what you find is that who gets their decisions flipped if you apply this model? It's the people that the model thinks are likely to be female and we're just below borderline. And that includes a lot of males. In fact, it includes as many or more males that are benefiting, just because there's more males overall in this particular applicant pool than it includes women. So a lot of our flip decisions are just canceling each other out. We're flipping men to negative and men to positive and women to positive, and we're actually hurting some women. Women who otherwise would have been accepted are rejected. And what is the reason why they're being rejected? Because they're just above borderline in the first place, but they're considered, based on their non-protected traits, to have been more likely to be male. And so this is problematic because—
sorry to interrupt, but I'd like to leave a couple of minutes for questions. So if you could wrap up pretty quickly.
Yeah, this is great. The very end. Great. So, what happens here is that we've sort of lost sight of the actual social context. We focused on this kind of parity, but the result is that you end up getting a model that's making decisions in this strange way. And it turns out that the feature that's predictive of whether you're likely based on your the non-protected covariate that's predictive of gender turns out to be interest area. So you end up doing is taking individuals that want to go into the areas that have a disparity, that most need to be diversified. And you say, because they want to go in that area, they're actually likely to be male. So now we're going to hurt those individuals. So it's the people who most need to be helped that are hurt. And the people in the maybe most already progressive or most already sort of along their way areas that are then benefiting. So you have to be really careful of this context. And it's not enough to just sort of fixate on one of these things and call it a definition of fairness and lose sight of the actual social context and the set of incentives and precisely who is being hurt or helped and whether or not the process makes any sense. So I'd like to just end by saying there is a lot of interesting work that attempts to go beyond just statistical parities conceptually. There's a line of work in causal fairness that I think is conceptually interesting, even if it maybe doesn't give us the most actionable tools. There's also a line of work that I really like from people like Lily Hu and Smith and Milley and Moritz Harslab, where they try to start coming up with models to get at least qualitative understanding of the kind of long-run dynamics of applying these policies, and are they actually hurting or helping people, and how do they influence people's behavior if you distort a landscape of incentives. So that's my entire talk. I'm super grateful to the organizers for their heroic patience with my inability to pre-record things, and happy to take any questions. Thanks.
Thanks, Zach, for a great talk. So I think we only have time for one question. So I'm just going to take the top voted one on the QA. You can also feel free to answer the rest of the questions in text later, or you'll have more chance to discuss also during the panel at 1 p.m. So the top question is, how do you think we can deal with the problem you raise of researchers losing sight of the main problem their algorithms are trying to solve, often proposing solutions that are really more like deflections? Do you think maybe conference or journal reviews or an independent auditing committee or government regulations?
It's a good question. I think there's a lot of kind of points to tackle that, right? I think one is the point of researchers naively proposing solutions. One is the point of people actually taking actions. And I think, I don't know that I can give as comprehensive an answer as I'd like to without running over. There are, I think, a few small things. Like I think, like this point about conference journal reviews, something that I think we don't do enough is that machine learning is sort of very cavalier about sort of trespassing into other areas. And overall, this is something that I like about machine learning. I think that there's something nice about the way that we're not very doctrinaire about our disciplinary borders. I think we need to be similarly cavalier about who we can script to review. And like if we're going to expand the borders of the field such that we suddenly say that work addressing a certain set of normative problems is part of our field, and we're not going to like that means that like we can't just you can't have a paper someone saying like I propose the ethical agent that now will always comply with ethical principles when you deploy it in the world to solve some kind of problem. And then all the reviewers only know about reinforcement learning and are sort of unable to call bullshit on the kinds of goofy statements that might be made that are just sort of outside of their I think in general, like that's one side. Another thing that I'd point out is that there's sort of overall, like, I think it needs to be a kind of attitude of just taking these problems seriously. Like, I'd point out that there are spheres where people take extra statistical concerns seriously, and one of them is profit, right? So if you come up with your goofy like recommender system that's predicting the wrong thing and doing everything wrong, and you go to Google and say, I'm going to change how the ad system works because my model got a better AUC, then nobody is going to actually say, okay, we're going to convert our entire like $1 trillion company over to your algorithm, or all from, and change. So what they say is, okay, we're going to start doing experiments in the world. We're going to, okay, it's nice that you did good on this offline algorithm, on this offline performance metric, but they're actually going to deploy it and they're going to do like a web lab or an A/B test and start seeing what is the impact of this policy in the world. Are we making more money on those customers? Or are we making less? So when people's profit are on the line, companies are actually really good at saying, kind of taking a step back and thinking critically about, is this actually doing what we want from a standpoint of making profit? And I think people need to apply a similar level of seriousness to concerns that aren't just about their profit, but about the impacts on the lives of people that are subject to the decisions that we're making.
No, that makes a lot of sense. Hopefully those are things that we can start to incorporate into our publishing in conferences and journals. So thanks again, Zach, for a really great talk. This is clearly a topic that a lot of us care a lot about. And please do answer the rest of the questions in the QA in text. And so now we're going to show some videos from sponsors Huawei and Amagia before our next talk.
All right, great. Thank you.
At Amagia, we gather creative minds to reimagine healthcare and reveal the full picture of personalized health. By creating a collaborative ecosystem of the best clinicians and AI scientists, we are able to tackle some of the biggest challenges in healthcare today.
Welcome back to from this very short break with sponsors. So we are now back to our initial schedule with our next keynote by Irina Risch. So for those of you who don't know her already, Irina is an associate professor in the Computer Science and Operations Research Department at Université de Montréal and a core member of MILA. Her research focus is on machine learning, neural data analysis, and neuroscience-inspired AI. Her current research interests include continual lifelong learning, optimization algorithms for deep neural nets, sparse modeling and probabilistic inference, dialogue generation, biologically plausible reinforcement learning, and dynamical systems approaches to brain imaging analysis. Before joining UDM and MILA, Irina was a research scientist at the IBM T.J. Watson Research Center, where she worked on various projects at the intersection of neuroscience and AI. So with all of this, I wouldn't be surprised if you all probably knew her already, since she was all over the news in the past weeks. So I'm not going to keep you waiting more. Here is her talk. Welcome, Irina.
Well, thank you so much for inviting me. And I guess just as Zach, I'm going to give a live talk, which wasn't pre-recorded. So let me share my screen right now. Okay. Just a second. Can you see my screen? Okay. Just a second. Okay. Okay, you can see my screen well? Okay, hope so. Okay, so I wanted to give a overview of different research topics that we were exploring recently, and not just us, but many collaborators, that probably can be unified by this common goal of going towards somewhat less artificial AI. And what I mean by that, as we all know, despite the recent advances, impressive advances in various applications of AI, from playing chess to Go to self-driving cars to generating pictures that are sold at auctions in New York, and advanced translation and also language processing. Besides, beyond all that, we still have this main limitation everybody keeps talking about, that AI is still quite narrow. It's a narrow specialist instead of being a versatile, kind of a broad human being who can learn all these different tasks, maybe not optimally, but can switch among them very quickly. So one of the most frequently cited issues with AI and deep networks particularly is their sensitivity to attacks. For example, adversarial attacks that are not really noticeable to human eye can be really devastating for the performance of deep networks, as we know. And that goes about different kind of unnoticeable for human eye noise that can be added on top of pictures, or changing between the train and test conditions. Another type of brittleness or lack of robustness is a well-known inability of most today's AI systems to generalize out of distribution. And this is classical example from well-known invariant risk minimization paper, and the talk by Kartik, who is coming as to join us as postdoc, hopefully in January. Classical example of classifying different animals, for example, cows versus camels and so on, where background may change, but your deep network can extract features that are sensitive to spurious correlations between the type of the object and irrelevant things such as background. So if it learns from pictures of cows on green pastures, then it may have hard time classifying correctly cows on the beach, for example. So on and so forth. What we're trying to do here is to see whether we can go from current neural networks that are very rough approximation of human brain, which are still somewhat static statistical models, essentially kind of following the tradition of machine learning and classical statistics, and comparing it with brain, which is complex, multivariate, dynamical system, which is always active. And there are many more inductive biases in the brain that perhaps could have been used to improve our artificial intelligence and make it less artificial. So overall, there are multiple aspects on this road from current narrow AI to the future general intelligence, but the ability to learn from multiple tasks, to be broad, is definitely one of them. Ability to be robust to perturbations of the environment, and perhaps incorporating more biases, more constraints, more regularization from neuroscience can help us advance those capabilities. Okay, so let's start with robustness. Just to give you a quick example, this is a classical problem where you assume that your clean data may be perturbed slightly, and your goal is to figure out how to train models that will be robust to such perturbations. And there are different types of adversarial attacks, but essentially you don't want to be too fragile to small changes in the input data. no matter how they're done, you still want to be able to, for example, recognize this image of cat as I showed before, and not confuse it with something totally irrelevant. There are prior approaches, for example, trades papers that came out last year, and many others, which essentially focus on regularizing the empirical risk that you use to attain accuracy on your clean data with some additional constraint or kind of part of the objective that is focused usually on trying to make prediction more robust. They focus on the objective of the task, on the prediction, rather than actually focusing on trying to learn representations, intermediate representations that are more stable to changes in the environment. And that's exactly where our recent approach proposed by my former postdoc, Poya Bashivan, and this paper is currently on archive and in submission. The idea was kind of simple, trying to say that maybe instead of focusing on the final objective, classification, and trying to make that robust, let us focus on trying to learn representations or features that are not sensitive to the input perturbations. And to use that, you can try different approaches. Particularly, we propose to use additional objective that stems from adding adversarial game, GAN-like kind of discriminator on top of those representations, and essentially trying to push them towards representations that will not be sensitive or will be robust to attacks applied to the input images. And as a result, well, the algorithm essentially, as I mentioned, mixes the objective of prediction, the empirical risk, and that adversarial objective with introduced decoder that tries to discriminate between representations corresponding to clean images versus corrupted images. As a result, this kind of simple approach performs quite impressively well, especially when the strength of the attacks increases. And we tried different data sets, we tried different state-of-art methods, and essentially what we see here is that methods that are aimed at the final goal, classification, being robust to attacks, seem to be much more brittle than our approach that focuses on learning representations of features that are not sensitive to those attacks. So basically there is quite impressive difference, and we see that the green line, our approach, does not break or breaks much later with increasing strength of the attack. Another topic that I touched upon in the beginning is that another desired property of the artificial systems that we would like to achieve is being broad, being able to solve multiple tasks, potentially being able to solve tasks during their never-ending, continual, or lifelong learning process. And that is one of the kind of domains of continual learning. That's a field, very popular, very actively researched field, where we go beyond the standard machine learning setting of training your model from one data set, and we go into more realistic, continual, lifelong learning of models from stream of non-stationary data, where the different tasks will come your way and you will have to learn new tasks to adapt to them without forgetting previous tasks. Unfortunately, if you use plain vanilla approaches such as SGD or whatever advanced methods for learning neural nets, you will experience what's called catastrophic forgetting. And catastrophic forgetting essentially is an old, well-known problem, even from neuroscience, where it goes under the stability plasticity dilemma name, and essentially means that when you adapt your parameters of your model to a new task and you don't take any extra precautions, then you essentially change the model to the point that it will not be able to perform well on previous tasks, on what you learned before. And it's interesting also that continual learning is kind of most challenging setting, closely related to many other modern popular areas of research, all based on the notion of trying to attain some ability to be broad, to learn from multiple tasks, whether it is meta-learning, online learning, domain adaptation, or transfer learning. All those domains closely relate to continual learning, but continual learning has additional challenge, which is also more realistic, to be online learning. That clearly relates to applications such as self-driving cars or robotics, or any kind of interactions with human in real life, because all of them will be temporal, will be online. And I just wanted to mention also recent work by my colleagues from Mila, led by Massimo. And this is an attempt to propose a novel framework that would be unifying different recent approaches to continual learning, such as meta-continual and continual meta-learning, and extend the standard settings to the more realistic and challenging setting where the task shifts can be sampled stochastically from environment, where task boundaries are not known. It's so-called task agnostic setting. And essentially there is some hidden context which defines what target distribution you're gonna get, and so on and so forth. So basically, this is more general and challenging setting, which subsumes, you can show how that kind of setting subsumes the key recent developments along the lines of dealing with multiple tasks and data distribution, such as meta-learning, and as I mentioned, meta-continual, continual meta-learning, and so on. And the approach we use builds upon the famous MAML used for meta-learning, and just kind of modifies it to work in the continual learning setting. And essentially, it's based on pre-training, and it's still a realistic assumption because you're probably not gonna let a self-driving car go in the wild without pre-training it for extensive period of time. And it also relates to robots and any other setting. So the pre-training phase makes a lot of sense here, but then the framework will allow you to quickly adapt to new tasks without completely forgetting what you learned before. Essentially, it allows for fast remembering. And empirically, we don't have much time to go into details, but bottom line, is that results are quite promising, and they were obtained on multiple imaging data sets, and more details can be found in the paper. Now, I would like to change gears and actually address more fundamental conceptual topic that I mentioned in the beginning, the topic of more biologically plausible and more neuro-inspired approaches that perhaps can really enrich the current field of AI and the set of algorithms and models that we use. It's needless to say that there is a huge difference between what we have right now in deep learning and what we have in biological brains, starting from such things as basically real valued activation propagation in our models versus discrete spikes, synchronous computation versus asynchronous, the single time scale we use in deep net training versus multiple time scales, so on and so forth. So we're still far from having modeled some essential properties of the brain that might be actually the key to the broad, robust, and in general, much less artificial intelligence. And there is an interesting paper that came out last fall about engineering a less artificial intelligence. Essentially, it also makes this point that despite all the recent successes with scaling neural networks and achieving quite impressive results, we still believe that inductive biases that you can borrow from neuroscience and biology may really help you advance the field to the next level. And this is an interesting debate question, and I think it deserves a panel on its own. But it seems to be that just evolving from scratch AI on practically infinite amount of data with infinite amount of compute, while plausible, may be still less preferable than using some good inductive biases that we could incorporate in it, borrowing them from biology and neuroscience. And in terms of what neuroscience can do for AI, there are multiple things, and we explored various avenues of research and other people as well. But just to name a few things, definitely the algorithms we currently use, such as backpropagation, are not only not necessarily biologically plausible, but also could be improved potentially using observations from how neural activation behaves in the brain. I'll briefly touch upon those intuitions and work that came out of that. Also, the ideas about plasticity of the brain, whether it's neurogenesis or other types of plasticity, can give us better approaches to continual learning. I will briefly mention it as well. Okay, so just a quick example, since I only have probably a few minutes left before the questions. I just wanted to mention that the workhorse of deep learning, backpropagation, actually has its flaws as well, as it was pointed out multiple times. Computational flaws include vanishing or exploding gradients, difficulty handling nonlinearities which are non-differentiable. For example, if your spikes are binary and you would like to model that in embedded AI in hardware, like on your basically where the energy you need energy efficient computation. And also it would be nice to have the cross-layer parallelism, just like it's happening in the brain. And there are multiple things about backprop that are not biologically plausible. I'm not going to go there in detail, but definitely the error feedback in them in the backprop doesn't seem to influence neural activity, unlike what happens in the brain. And weight updates are not local, and there is a long list of those issues with comparison of backprop and biologically plausible ways of error propagation in the brain. So just to mention briefly, we proposed last year an approach that kind of continues the tradition of target propagation work that both Jan LeCun and Yoshua Bengio and others worked on, essentially introducing activations as explicit variables and introducing alternating minimization approach, which actually helps us parallelize computation across layers, which resolves the issue of activations not being involved in the error propagation process, and also the issue with non-local updates. But unlike the previous approaches such as target prop, this flavor of alternative to backpropagation actually was showing promising empirical results, meeting the performance of SGD and Adam and sometimes beating it on several benchmarks, especially in the beginning, which also gives us idea that maybe such approaches could be used for good initialization. And perhaps I'm running again out of time, but I just wanted to mention another neuro inspiration that led to interesting kind of development in terms of continual learning or the adaptation without forgetting. And that was the wealth of research in neuroscience on so-called adult neurogenesis phenomenon, which actually, contrary to earlier wisdom, was showing empirically that in mammals, of course, a lot of it in rats, but also in humans, there is still the process of new neuronal growth in particular areas of the brain, such as hippocampus, which is specifically responsible for forming short-term memories, and to some extent works as autoencoder. And the question was both ways. Can you provide a computational justification for why this process is still happening in adults and why it's not enough just to change the weights in the network, as well as see if this can be used as a foundation for novel approach to non-stationary continual learning setting. And again, without going into too much detail, essentially you can incorporate birth and death of new neurons using for death group sparsity that kills multiple links and the neuron together, and the random process of generation of new neurons. And essentially when you have such more flexible expanding and compressing network, you end up indeed not only adapting better to new environment, better than the fixed size network of the same size, but you also do not forget and actually perform better on the previous tasks, as we showed in our paper a few years ago. Finally, these ideas could lead us to think about what could be, in general, approach to continual learning, where you potentially may have tasks or functions to approximate coming from infinite set of functions of some kind of world which has some structure, some constraints, and this family of functions hopefully has some finite basis that can approximate any of those functions really well. And then the second hypothesis would be that you could come up with approach that can help you incrementally learn the set of those basis functions and then combine them in perhaps nonlinear way to solve any possible tasks that will come your way in the future, as long as this task or the function to approximate comes from the world where you evolved to deal kind of with the environment. By analogy with the brain, where actually different parts of it or different basis functions evolved over millions of years to solve different tasks and be recombined to solve complex tasks. By analogy with that, perhaps we could try also evolve architectures of neural networks and hope that we're going to converge at network that can be sufficiently versatile. In a sense, it complements the recent interest and progress in terms of modeling independent mechanisms and recombining them in the real time with attention mechanisms, what Yoshua Bencho usually talks about. But what remains to be seen, how do you build this library of independent mechanisms? And the answer is perhaps by exposing your agent to sufficiently rich and sufficiently versatile set of environments. And essentially, I kind of wanted to just give a high-level comment that you can think about this continual learning in general along two axes. That environmental complexity is important, and learning on very simplistic benchmarks may not necessarily lead to interesting advances, because if environment gets more and more complex, you will need representation capacity of your models to match that environment. And while you can get away perhaps with a single relatively small neural network and just to change your algorithm for weight updates and handle changing tasks such as rotated or permuted MNIST, you won't be able to do that once the tasks start going beyond kind of very closely related distributions of data. You will need to grow your library of subcomponents, as I mentioned before, and perhaps eventually, hypothetically, you might not even get away with your current second generation neural nets, which are still, as I mentioned, static models with fixed set of parameters, which is very far cry from what brain is. Brain does not wait for the input of an image to update its weights, and that sit quietly waiting for the next input. Even when you sleep and you don't have necessarily any direct input, you're constantly active. So you have this complex dynamical system that never ceases to be active, and it's also well adapted to represent environment that's also dynamical and exists in time. So perhaps, that's an open question, we may need to switch to more powerful type of models that will incorporate this notion of dynamics and time in order to model the realistic environment. Okay. Well, just to play devil's advocate, I wanted to note that there are different opinions about how should we reach AGI, and there is clearly lots of success recently with simply scaling to humongous size existing models, such as, for example, the famous GPT-3 that is indeed truly capable of doing amazing things, provided prompts. It can write essays, or it can even write Java programs and do many other interesting things. It has humongous number of parameters, and it's been trained on large part of the internet. So scale seems to work. But the question is, does it mean that you don't need any inductive bias anymore? Is it inductive bias versus scale, or maybe it's both? And I think that's a good question. I subjectively still think that inductive biases, based on what we know about how brain works, can significantly improve what we can do with AI, or at least can kind of limit their computational cost by introducing those biases instead of making systems learn them using humongous number of parameters, humongous amount of energy and compute, and humongous amount of time. But as a last slide, and I'm going to take questions, we could always ask GPT-3 what actually it thinks about how we should go about achieving AGI, and is it just scaling transformers, or is there any better way? And here is the actual answer from GPT-3, which was quite insightful, I would say. Basically allowing AI to recursively create itself. And in a sense, again, one can argue applying the ideas from evolution here. So perhaps GPT-3 would agree that inductive biases from nature are useful, such as evolution. Thank you.
Thank you so much, Irina, for this great talk. Yeah, you covered a variety of aspects at the intersection of AI and biological intelligence. And this has raised a few questions by some of the attendees. Maybe I can go through them, and yeah, I can moderate a bit the Q&A. So when you were speaking about continual lifelong learning, it has raised the questions about like a pretty technical questions regarding the kind of architectures of neural networks that would be required to do realistic continual lifelong learning. Do you think that the kind of architectures that we are currently playing with are good enough and what we need to achieve this? Or do you think that we should be more creative and come up with different architectures because we are getting limited right now by the existing architectures that we're considering?
This is a great question. Thank you very much. That's why I put that slide at almost at the end, where I was trying to say that with existing architectures, I mean, there is this trade-off between the complexity of the environment, variety of tasks, complexity of tasks, basically what you're trying to capture, and the model capacity, representation capacity. And that's why I was saying that depending on how much you challenge your lifelong learning system, you may or may not get away with existing architectures indeed. So for relatively similar tasks, even not necessarily extreme case of rotated or perturbed dominist, even for different type of natural images, they're still not sufficiently different as opposed to maybe training your system on to do image recognition and then speech recognition and then text generation. So something as extreme as that, even so far, GPT-3, which is quite versatile in terms of tasks it can do, it still does not extend its capabilities to very different types of tasks, which are not related to natural language. And I think if you want to do that, the capacity of the model will definitely have to be in some sense larger, whether it's just a larger architecture, or maybe, as again, I was hypothesizing, I have this feeling that to truly represent dynamic temporal nature of the world, you may need to match it with dynamic temporal model, which definitely has much higher representation capacity than a static network. And the simple explanation is like hidden layer of size n can represent 2 to the n different inputs. If you take sequence of activations into account, you already have n factorial. And if you take timing into account and do time coding, you have much more representation capacity. And perhaps you will need that to truly capture the richness of our real world. Again, just a hypothesis.
Okay, so now you're talking about capturing the richness of the real world in terms of the architecture, which leads me to another question that was asked about continual learning, about the state of the art. Like it seems that the papers often end up experimenting on datasets like MNIST. Do you think that the current benchmarks allow us to capture the richness of the problems that we would need to develop the architectures that are rich enough to adapt to these kind of problems?
Again, another great question. So I guess the answer is, if you just limit yourself to this narrow benchmark, the answer is no. And that's why the most interesting, I think, area of continual learning, to me at least, is continual reinforcement learning, where the benchmarks are getting much more complex than simple image recognition, where you have to play different games or basically deal with different environments. So I think continual reinforcement learning is, of course, much more challenging, but also much more realistic and much more promising direction for developing such capabilities.
Yeah. I mean, I love reinforcement learning, so I'm very happy that you're saying this. I'm sure a lot of people here are happy to know that their field is maybe going to be the field that is going to push.
Life is reinforcement learning. The reality is reinforcement learning. It's all about reinforcement learning.
Speaking of reality, do you think that at some point we can achieve capabilities like imagination with neural networks, or are these systems always going to be stuck in reality?
I'd like to believe that the answer is positive. And actually, again, imagination, just like intelligence and other kind of key terms we use in machine learning, are at the same time not quite well defined. So I think it depends on the type of tasks you want the kind of, but in a sense, you can already say that if a computer can generate a painting and the painting is sold at the auction, like the last year, the GAN generation painting and so on, is it creativity? If computer can generate music, again, OpenAI seems to be really doing cool things recently. And I mean, in terms of creativity, yeah, that was yet another kind of approach they used to like generate music to basically compose and create songs. So it's pretty much, depending how you look at that, we may say we're kind of already almost there. And I think it can only get more sophisticated, again, due to perhaps scale, but not just scale. I still believe that scale is not everything. There must be some bias, some structure. And that's really important. So if you think about nature. If you just take wrong architecture and scale it and you get, I don't know, dinosaur brain or the whale brain, it's going to be huge, but still not as intelligent as maybe smaller brains with proper structure as us humble human beings.
And so we'll need to bring those inductive biases in our systems in order to be able to do as good as those smaller brains that are very smart. But how do you see, like, do you see a problem between like balancing how we incorporate the inductive biases in order to like avoid the brittleness of hard-coded solutions? Like, can we do this without having a bunch of handmade rules in our systems?
Right, yeah, and that's, I think, you can get perhaps to those biases. Well, of course, I mean, the neuroscience paper that I mentioned and similar work, they often assume partially what you're saying, not hand-coded rules, but perhaps you try to match, say, the activity recording in real brains, like in monkey brains, to the activity in neural networks. There are multiple papers on that. And as I mentioned, my collaborator, Poya Bashivan, had a paper on that last year with MIT colleagues. There is work in the area of trying to align activity in artificial neural nets with observed data in real brains, hoping to constrain and learn better artificial neural networks. So this is already not hard-coded rules. And structure, architecture, well, that is also something you can try to maybe borrow from the brain architecture. It's not exactly hard-coded rules, but still you may say that it's somewhat kind of engineered architecture. And the third way, I think most attractive way, most promising, this kind of evolving more complex networks through exposing them to properly kind of constructed environments. So basically you create smarter systems by something like curriculum learning, by something like exposing them to sufficiently rich environments. So it's almost like with kids. So I like this analogy between kind of building better AI and growing kids, because depending on what they will be exposed to in terms of environment and challenges, they may or may not develop certain capabilities, and you don't have to hard code the rules, but you have to give a good example or make them solve problems that stretch kind of their capabilities in orthogonal directions. So if you take this approach and maybe apply it to growing or evolving or continually learning systems, a properly constructed environment that is rich enough, but perhaps also structured from simpler to harder, that may lead to, it may be also, in a sense, create those biases, but they will be hopefully created just by evolution. Again, that's a hypothesis, but I think it's really important what benchmarks and environments you expose your models to and at what order, because they will learn kind of what they will be pushed to learn, in a sense. So if you show them rotated and missed, they're probably not gonna evolve too far.
So it's about crafting the proper training examples then, which is, I guess, linked to the fact that the existing models mostly stay within the training distribution. So you need to make that training distribution good enough. We had another question that jumps on this, asking how do we do well outside the training distributions? Are the causal models the only way to be good?
Another very good question. I love the topic of out-of-distribution generalization. And when I was talking about robustness, I kind of briefly mentioned the issues. I mean, this is at the core of machine learning, indeed, because while it talks about generalization, it's in the classical statistical sense of assuming that you train on the data coming from from same distribution, that test data, and that's what you call generalization. But we really need to rethink what generalization means. And in order to achieve out of distribution generalization, first requirement, you definitely have to modify your training to expose your system to multiple environments. And that IRM paper that I mentioned, invariant risk minimization, and multiple papers that came out on top of that, essentially they are all trying to introduce different form of regularization to make a model or particular representation more robust or invariant to changes in the environment. And adversarial robustness, by the way, also is closely related to kind of invariant risk minimization and out of distribution generalization. It's just environments are created not stochastically, but adversarially. And the question of causality is definitely closely related because if you manage to find the causal relationships, they are much more likely to stay invariant across variety of environments you're going to see. And there was also a very interesting recent paper coming from pretty much keep forgetting the group. Anyway, so the paper was about good explanations are kind of likely to be invariant, are likely not to change. From Bernard Shelkoff's group. Sorry about that. Yeah, so it was very recent paper. And essentially it's in line with invariant risk minimization games, and other approaches. There is also more recent risk extrapolation approach and so on and so forth. And this paper also goes into the same direction of building models that will be stable across multiple environments by means of different regularizers that you impose on them. But it also kind of discusses that the true explanations that capture the reality, they will be probably causal explanations, and they will be more stable ones. I don't want to say absolutely 100% that you cannot come up with robust invariant representation and model that is not necessarily causal. I don't know. But there is definitely lots of overlap, and it's much more likely to get robust and invariant model if you get causal one. So aiming at discovering causal mechanisms is clearly an important goal.
Thank you so much for all these insights on all these different topics. Clearly, people would be interested in keeping hearing from you. We still have questions coming in, but if you want to keep tight with the schedule, we'll have to stop the Q&A now. But if you want to answer those questions over chat using the Q&A toolbox, if you have time this afternoon, feel free to. I know people would be very happy about this. Otherwise, if you are also free to come and hang out in Gathertown in the poster session and social at 3 p.m., then people could find you and they could come and they could keep asking you questions about inductive biases and the quantum fuzziness of the brain and all those very interesting topics.
I didn't talk about quantum on purpose. People asking those questions.
Well, thank you a lot, Irina.
Thank you so much for inviting me. And yes, I'd be happy to answer questions offline. Just let me know, maybe through Slack, where to go. So I'd be happy to do so.
Perfect. I'll see you later.
Okay, thanks.
All right, thank you, Irina, once again. And so we will have a shortish break of half an hour, or 28 minutes to be precise. At 1 p.m., we'll have the panel here. We'll have Irina, Zach, and Natalie on the panel, and it will be moderated by Abhishek Gupta. So go have some lunch and see everyone here back at 1 p.m.
All right. Hi, everybody. Hopefully you guys can see me and hear me. Good to have everybody here participating with us virtually this year at the Montreal A.I Symposium. So thank you for attending. Should be a very, very exciting panel today. We are going to be talking about ethics, fairness, and bias in AI, something that's been coming up quite a bit over the past couple of years. I think what better opportunity than to talk about it in such an interdisciplinary panel where we have with us today a veritable set of experts, really. I don't think any of them need any introductions, but I will make very, very brief introductions nonetheless. So first off, I guess I'm Abhishek Gupta. I am the founder of the Montreal AI Ethics Institute, which is an international nonprofit research institute that focuses on applied technical and policy measures to address ethics, safety, and inclusion in AI. I also work as a machine learning engineer at Microsoft, where I serve on the responsible AI board for my organization. And I guess without further ado, as I said, I think our panelists don't need an introduction. I said to them as much in my email, but I will just say a few short words about some of the work that they've done. So with us today, we've got Irina Risch, who is an associate professor in the Computer Science and Operations Research Department at Université de Montréal. She is primarily focused on neuroscience-inspired AI research, and just a few days ago, there was a big announcement of a massive grant that she's been awarded along with her team at the university. So congratulations to her, and really looking forward to hearing what she has to say. Then we're joined by Natalie Schluter. I hope I did not butcher her name. She is a senior research scientist at Google Brain and an associate professor, joint lead of NLP North at the Department of Computer Science, IT University in Copenhagen. She is also the first diversity chair, I believe, for ACL leading up to 2022. So quite excited to hear what she has to say about all the things that we're going to talk about today. And finally, we have with us Zach Lipton, who is an assistant professor of operations research and ML at CMU. He is a very, very fascinating individual. I've seen him speak many, many times. His Twitter feed is one to die for. So if you don't follow him, please do. And one of his papers that I really love is Troubling Trends in Machine Learning Scholarship. Again, if you haven't read it, a must read if you do any sort of research, want to produce meaningful outcomes. So that's really it. What we will do, just in the way of the format for the panel today, I have some questions that a lot of you contributed, so thank you for doing that. So we're going to spend about 35 minutes going through some of those questions. I will leave about 10 minutes for our live audience, and live in this context being virtual, because that's the best that we can achieve. And then finally, we'll leave about 10 minutes for open remarks at the end from each of our panelists, or keep the questions going depending on how everybody's feeling. Fantastic. So I guess we'll get started. The first question, we're talking about ethics and fairness, and this is one of the contributed questions from the folks who had filled out the survey, was, and I'll read it out verbatim, will society manage to responsibly manage the use of AI impersonation and fakery technologies as they continue to advance and progress? If so, how? If not, what can we do to mitigate the harms? So Natalie, I see you're unmuted, so why don't we kickstart with you?
So it's a very important question, and the answer is, for me, that I don't know. I don't know if society will succeed in managing to use AI responsibly. My guess is that if there is no sort of check that it's being used responsibly, that probably not. The main problem with this, in answering this question, is that, like, I'm not a sociologist, I'm not an ethicist, Just like most other people in my field, like I don't have very good ideas about social dynamics, about ethical consequences, and that's a problem. So I remember, you know, from the other point of view, I mean, talking about ethics and talking about societal consequences of technology also requires, you know, people like me who are making the systems. I once went to an ethics panel, or was invited to join an ethics panel. It was a national panel on AI, and I was the only, you know, person doing any sort of artificial intelligence there. So I mean, the panel was mainly full of journalists who wrote about science and some politicians. And this is another big problem. I went once to the panel, and then I kind of left again because I couldn't understand what anyone was talking about. And so we definitely need this interdisciplinary, you know, working together with all of the specialists, with the sociologists, with the ethicists, with the computer sciences, because we don't know everything. A sociologist can't really tell us what data is capable and what algorithms are capable of doing, or predict what they're capable of doing. So yeah, one thing I just want to mention is that I mean, a lot of the responsibility in society, I mean, historically used to be on, you know, sorry, not politicians, but journalists and academics. And this has kind of changed recently. And I think that there is some push now in our field to start this up again. So for example, realizing that what we do, I mean, even the smallest stuff in NLP, you know, there's only systems in NLP that actually work very well for one sort of dialect of English, and for everything else, it's kind of splitting society. So let's just get, you know, real about what we're doing here, have some understanding, and require that there is some ethical consideration about the technology that we're developing at publication time and at product development time.
Absolutely, those are such valid points, and I think it's really important to have sort of representation from folks coming from different walks of life. Not, you know, of course, including folks like us who, you know, do technical work on a daily basis, because all of the measures that we build, I guess, need to be rooted in practice and you know, the science and engineering that goes behind it. Zach or Irina, I don't know if you want to chime in and respond to what Natalie mentioned or build on it. Irina, yeah.
Well, I completely agree with Natalie that we need more interdisciplinary team for that, because it's even hard at the time of publication to kind of imagine all possible uses of what you're proposing. And it's indeed can be completely your responsibility if you propose particular approach or an algorithm and it may be applied in certain way that you didn't even expect. It's hard to put all the responsibility on AI researchers, because they definitely need kind of experts from other fields, especially from indeed ethics and philosophy and perhaps law, and people who kind of deal with this type of issues in other fields. So that's I think is really important, because I don't think that we AI nerds might not be able to do it on our own.
As much as we wouldn't like to hear that, but that is the truth, I guess, that we can fix everything. Zach, you want to?
Well, I guess to bring back to your original question, you kind of started off by speaking about the potential of things like deepfake and sort of language models to find kind of maybe misuses and creating fraudulent information, or and I think, you know, it's worth separating out. Like one thing that I think often happens when we get into these weird spaces. We've got a set of concerns that are related but are different kind of category. Like there's a set of technical concerns, like is it feasible to develop a technology for authenticating video such that you know, we can not enter a space where like there's a fear for, you know, democracy and the dissemination of information if there's like no way to sort of ever establish like the veracity of a recording or of a document. So there's a technical question there, which is like how can you, in the world where someone could develop sort of perceptually believable video and maybe even match someone's writing style, sort of in a way that's sort of easy. I think we've always been able to create fraudulent documents. So I actually thought the emphasis on, say, like GPT-2 was a little bit misplaced, because that never seemed like that was the primary obstacle to the propagandist, was the inability to write in somebody else's voice. On the other hand, the ability to create seeming like video or photographic evidence that's not real is dangerous and has already been used as a political weapon. So there's a technical problem, which is, can we develop technology such that in a world where someone can do that, we still have some other way of verifying the source of video? And if you have, then there's like the set of regulatory concerns, and these are coupled because they're coupled by feasibility. It's like ultimately your ability to design functioning regulation is designed on like what things are enforceable and what things, what kind of technology does the state have available to sort of like bring to bear. If there's some alternative way of verifying things, you could require that, you know, that steps are taken. If there exists no such technology that can establish the veracity of a video, this sort of ties the hands of people who might want to regulate that technology. So, you know, I kind of agree with everyone. I think that there are technical concerns, there are normative concerns, there are trade-offs that are not in the space of the technology, but in the space of kind of societal kind of priorities. And I think the main thing we need to do is be really clear about these issues. What are the normative concerns where we need to think about them in a guided by ethics? What is the landscape of technological possibilities where obviously we do need the input of technological experts? And I think, you know, at least now the situation is actually quite a bit better. Natalie spoke about these sort of interdisciplinary venues where people actually are meeting across disciplinary lines. I think in some ways that these have been more mainstreamed over the last like 4 years. Like I know that when I started writing about these issues in 2016, I didn't know many people who were coming at it from, you know, maybe more like iSchool or philosophy or legal type backgrounds. And I actually found them, there were like these small workshops that were happening in different places. There weren't conferences like Fat Star and now Fact that, you know, kind of bring these people together. So I think, you know, those channels are opening, but they're still maybe often drowned out by the like lion's share of like sensational coverage of the media, which is talking to people that aren't participating in those kind of interdisciplinary spaces.
Right. Natalie.
I think that we also have to be careful that with regulation, I mean, comes creativity. That there's always going to be a new challenge for every rule that you make, that people will come and meet with new, different ways to do something very nice or very, you know, awful for society. So I think as scientists, we should be happy for these new challenges and very aware of them at the same time, because that's kind of what makes our job interesting, that things are always moving and we're always, you know, finding new ways to actually help make society better, if possible. And also, you know, yeah, I think we should just be aware that there's always coming new ways to do bad things. So even if we do make rules, there will come something on the other side.
Right. And I think, you know, sort of building on that, one of the things that has been interesting is that the tools are becoming more accessible, so that there's a wider set of people who are able to apply them without maybe even, you know, doing fundamental research and such. But at least they're able to operationalize and use those tools to, let's say, propagate, you know, impersonations, fakeries, and all of those manners of things. So if we were to talk about it from the perspective of publishing norms, let's say, how would you how would you approach that as researchers, as practitioners? For example, with GPT-2, they approached it from a staged release process, and they documented their sort of thought process as they went along. They did some bit of research in terms of what potential negative consequences could arise as they released larger versions of the model. Do you see that as being something that is an effective mechanism, let's say, for preventing some of these harms?
If you're looking to stir the pot, I could jump in here. I'd say no. Like not saying that I don't think we not from a standpoint that I'm like opposed to that kind of process if I thought it were effective, but more just from a standpoint of efficacy. I think there's a way that we kind of lionize some people in AI and we think we're among geniuses or something, but actually I think it's a rather kind of workman-like field. Like it's a very incremental field. I don't think I can point to a single significant breakthrough that categorically changed, besides like small moments like maybe the ImageNet breakthrough in like 2012. But overall, these things like GPT-2 versus, whatever was the XLNet or whatever was like the slightly smaller language model beforehand, strike me as almost always completely insignificant in terms of the actual. So I don't know that taking any given paper and subjecting it as though any one paper is actually doing anything of note as far as society is concerned. It strikes me just from a standpoint, again, not that like if I thought really there was someone who was like, there have been moments in history, like when Leo Szilard realized that you can create a chain reaction by, the emission of uranium fission or something. And it was like, hey, let me scribble a note to the Curies and let them know that they should not share this information with the Germans and keep it out of Nature, Wissenschaften or whatever it was, like the big journal at the time. I don't think we're in possession of a great secret. I think that overall, we're a field that is like layering tips and tricks on top of tips and tricks, and any one of them by itself is insignificant. So it just strikes me that's not the right choke point.
Mm-hmm. And yet, creation of GANs kind of opened the door for all kind of deep fakes, right? So it's not exactly like example you gave with nuclear power, but yeah, so it kind of hard, it possibly was also hard to predict because, yeah.
And also over like a 4-year period.
Yeah. The problem, it's not always easy to predict with a paper, which indeed may look like somewhat incremental or maybe really cool idea and really novel, but still it's really hard to predict how people might possibly start using or abusing it, especially in a few years from now. So that's kind of a problem. It's almost you need an AI that's going to specialize on predicting of possible misuses of technology you just proposed. So maybe you need to start creating AI that will play a role of this ethicist. So kind of automate that as well.
Well, I think at the same time, we have to remember that it doesn't take like a huge discovery to do a lot of damage with the systems that we're building. And in fact, if I look at most of the papers that are submitted this year to ACL, for example, the biggest NLP conference, that I would probably find multiple horrible ways to apply them to be destructive in society. I mean, it doesn't take a lot of imagination, I feel. So maybe it's almost too open of a question, and maybe also the question is like, just by not mentioning all of these really awful things that you can do in society, does it still make it not bad? You know, I'm not sure.
Well, and I think that actually brings up an interesting point, and I know that there are other questions that I wanted to ask, but sort of picking up on this thread that you just mentioned, Natalie, one of the things that I think would be interesting to think about is when we're talking about some of these broader impact statements as they've been, I guess, mandated as a part of NeurIPS, and I believe iClear for next year as well, then, are those also sort of superficial mechanisms that don't actually do any good?
Well, I mean, I think it's much better than what we have had before, which was zero. So I think just even getting people to spend a little bit of time actually thinking about it is important. But there are, for some papers, there are specific issues that they need to address and that are not being addressed across the board. It's for a random few that happen to perturb a few people in the community are required to do some ethical considerations on their paper. But it should be, I think, more generally done in the field, in my opinion.
Yeah, I heard. I think it's an interesting question, the role that the broader impact statements play, and I've seen some interesting debates about it. I can convey like the gist of some of them from like Chatham House rules, sort of. But I saw one debate. I was like, very interesting. It's like both interlocutors like believing that these are important problems and that we should deal with them, but differing over like the efficacy of these statements. And one point is sort of like, okay, you have these statements and you have a bunch of people who have never in their lives thought about even the application of the technology, let alone the associated normative concerns, like chucking out like 4 minutes before the deadline a couple paragraphs to be read by a bunch of reviewers who also have never thought about the application technologies of these normative concerns. Like, how is this a solution? And then there's a rebuttal that I actually found kind of convincing. Just the rebuttal, and I think this actually speaks to what Natalie kind of hinted out, is the rebuttal that I find a bit convincing is sort of like, people don't think about these things overnight. So you send a signal by what you say is a mandatory part of the process that says, if you want to participate in this community, like this is part of, just like, when you evaluate PhD students, what you choose to make part of their, whatever it is, like their quarterly or semester evaluation. Like when you elevate, like if you elevate service and you put it on the page of this is what you're being evaluated on, you're sending a signal that this is a core value of the community. And I think that maybe that's the biggest role of the broader impact statements, is to say that this is a community that is concerned with it, that has elevated it to a consideration to be taken into account when your research is evaluated. And that's, it's not just like, you could be skeptical about what's in them and still think that it's serving an important purpose in terms of establishing community values.
Right. Very nice. Did you want to add something to that?
Well, I also was a bit skeptical about this efficacy of this broader impact statements as well. In many cases, and perhaps, well, to be realistic, yeah, the best we achieved so far is just indeed to send this message that you need to keep this in mind. But in reality, people were really, I agree with post Natalie. It's like most of the people were just doing it at the last moment, just because it had to be done. But maybe if it kind of stays there and becomes kind of part of evaluation, that starts kind of propagating the message that, well, it's there for a reason. But again, I mean, it's not probably going to really solve the problem at its core. And it's a really tough question, because as there was a comment, I think in the chat, there are several comments, and I just saw some popping up. Indeed, like you don't burn spoons just because you can take somebody's eyes out with a spoon, or like whatever you create, you can immediately think about potential misuses. So like, you think about chemistry, well, you can create chemical weapons. You think about physics, here we go with like nuclear bombs. So pretty much any science or technology can be used for good or for evil, and you definitely cannot ban everything, neither can you Yeah, so basically it should be some kind of really agreements or some kind of normative regulations, but it shouldn't be necessarily at the level of like creating this technology. It should be at the level, I think, of applying, because I mean, it's really hard to ask people who are focusing just on like core science or core engineering and coming up with algorithms also play the role of a person who thinks about ethical considerations, law, enforcing those. It's just like, I think it's just asking too much from computer science researchers and AI people. So there should be some more, I don't know, advanced mechanism in action, and it should kind of be more at the level of applications, I think.
Mm-hmm.
I think that, you know, in this first year where we're all, I mean, we're all starting to add these ethical statements or have it be mandatory in conference submissions. I think, you know, as computer scientists, we're just like, okay, we should do something. So let's make a space for this. And I think this will evolve like over the next months, next years. Just talking with like ethicists about this, I mean, they have a very structured way of thinking about these statements. They're saying, okay, you need to isolate your core values for the, I mean, these are things that we don't know anything about, but I think that there are ways to extract this information from authors by, you know, doing clever forms when they're doing submission and so on.
Definitely. No, those are all great points, and I think definitely something to keep in mind. I wanted to shift gears a little bit because there was another interesting question that had been submitted through the forum earlier, and that was around sort of a larger question in terms of framing ethical AI from a national or nationalistic perspective, and how that might create advantages or disadvantages for different nations. I'm sure, in fact, I think we've got representation from 3 different countries today. We've got Denmark, we've got Canada and the US.
Canada and the United States are different countries?
Oh, wow. Okay.
Very different.
Very different. As the Canadians on the call.
I was wondering why they wouldn't let us across the border.
Well, that and COVID, I think.
We can talk about that offline.
Yeah, I guess politics aside or not aside, do these different framings then, these different ethical framings and this competitive framing when it comes to AI research and development, does that offer advantages or disadvantages in terms of competitiveness to nations? And yeah, Irina.
Yeah, it is actually quite a tough question because it's similar to other examples when advanced technology can be misused, and perhaps it requires like multi-country agreements, just like with chemical weapons, just like with nuclear weapons, just like with any kind of technology that reached the point when it can have like severe negative consequences. It really takes some kind of agreement at the multi-country level, because I mean, of course, it's not always 100% enforceable and so on and so forth, just like with other things, just like with nuclear power. I mean, you cannot really make sure that nobody is developing it in secret if they agreed on paper that they are not, right? But at least I think if you again bring it to that level, to the level of the agreements, and there is also some clear incentives to follow, or at least avoid breaking those agreements, I don't know, some economic or other consequences. So you might not be caught, but if you're caught, there will be consequences, and they are sufficiently serious. So if it's something of that kind, that maybe indeed, if there is simultaneous agreement across multiple countries on some common kind of guidelines of applications of AI, that at least could be a partial solution. But I mean, your question, it's really goes, it's a deep philosophical question in general, and it's not just about ethical AI being adopted by one country while another kind of not adopting that and gaining advantage because they are not being ethical in their applications. And so it's kind of I know it's a tough question about how to potentially employ any altruistic reward function in multi-agent reinforcement learning system if the other players are not employing the same function. So I think it's an interesting AI problem, by the way, as well. So we may use some game theoretic approaches, but you really need to make sure that deviation from the kind of ethical rules should be not advantageous for those who do that somehow. So you need to design a game.
So maybe do something like Salesforce did with the AI economist. Maybe create some sort of a simulation and see what kind of
that's actually a great idea, because it's indeed, it's kind of gets complicated with multiple players and kind of this different like mixed games, non-cooperative games and so on. So basically, exploring this, I think it could be an interesting direction before you suggest maybe some recommendations to whatever committees, because it's hard to think in advance about all possible ways things can go wrong. So you need simulations.
Absolutely.
But in general, again, I am far from being expert in ethics or law or even philosophy, and that's why I keep repeating the same point that Natalie made. I think we need those people in this field. At least we need kind of some cross-fertilization. So we need to talk to ethicists and philosophers and people who kind of work on ethics, and that's their job. They're basically their job. So we need to learn from them. But indeed, we could bring in things such as game theory, simulations, and trying different scenarios, trying different policies. For example, we can come up with some candidate policies or types of agreement and see what could happen and how likely it is to be stable, for example, or it's kind of easily broken. So that's pretty much maybe where AI people can also help ethicists to make ethical AI better.
So I might take a, sorry.
No, go for it, Zach.
I might take a slightly different perspective here of like, you talk about the sort of nationalization or the sort of this rise of like, sort of national AI efforts and viewed through the lens of national competition. And, game theory is great when you have like something like a very, like you want to isolate like a very particular kind of incentive structure, understand how it affects behavior. But I think what we're dealing with here is a complex social system where I don't know that like we have like a refined set of, we know the mechanism and let's figure out what the strategy is. I think it's more, it's worth just thinking like, who are the players, what's going on, what does this even mean? Like, so my first gut reaction is like on the surface level, national competitiveness in AI seems pretty goofy, right? It seems like we have a community that has no secrets, that has no great like, guardable ideas. Like we have a body of empirical knowledge that for the most part is being just chucked onto GitHub in archive every single day. It's like, what does it mean? There's no moat. What does it mean Chinese AI versus American AI? So on one hand, I look at it and I think it's ridiculous. Then I think there's a more maybe refined look and say, what does it mean? And I think it's not just a question of like what's ethical. It's not like there's a central decision maker who's making decisions about ethics. I think like first there's to understand the social dynamics. Like what is the system at play? And it's like you have a bunch of governments, you have university systems, and you have a bunch of decision makers making, and you have a bunch of individuals that are whispering in their ears, and everyone has their own set of incentives. And what are the incentives at play? And I think there's a few big ones when it concerns national ones, priorities. One is a sort of sense of economic strategy. It's just a sense of like, they think this is potentially a huge industry. Countries don't want to be left behind. They want to have a talent force in their country, a labor force that's able to be competitive. And so it's a matter of like national investment I think more like a matter of building up skills for, the economy of the future versus the past. I think that's one drive of why countries want to invest in it. There's another side that I think we can't ignore is the militarization of technology. So why are you going to convince, ultimately, why do governments spend billions of dollars on technology? Like, there's a reason why it's like, if you look at the cone of expenditure, it's usually like basic science in the very center, life science is a order of magnitude larger, and defense spending is a order of magnitude larger than that. So, there are efforts, many efforts underway in many countries around the world to, in various ways, sort of weaponize this technology, either in terms of large surveillance systems or actual sort of like autonomous warfare. And that's something that we might be a little bit shielded from when we're just sort of the money trickling down to us to support basic research funding, some share of it, but that's part of, I think, a dynamic that's going on, and part of like a defensive mindset of people thinking, well, we need to invest in this so that we have, if this turns out to be a military strategy, we have, the ability to be competitive. When it comes to ethics, I think the problem is, it's not just a matter of we could just say like, oh, let's just bring the philosophers in or something, like, because it's not like it's worth thinking also just, it's like, who is we? Like, I think for the most part, it's, we have to sort of think about this more complicated system of like, who's making these decisions and what are they guided by? And is it ethics even in the first place? As for what to take concretely from that, or what any of us should be doing as concerns, that's a harder, and I don't think I have a great answer on the spot. But I think it is maybe good to be aware of these kinds of dynamics and the ways in which they're kind of maybe just the ways in which they're maybe just silly, and the ways in which they're maybe dangerous.
So, no, it is a good point. Yeah, it's just bringing in philosophers to define what we should mean by ethical AI is, of course, not enough. I think that AI people should work closer with governments to kind of decide on those regulations and things like that. So they should be just indeed really talking to governments, because it's as I said, it kind of similar to the categories of chemical or nuclear and other type of weapons. So it should be taken as seriously, and therefore, yeah. So how to do that, that's a separate question, but I think it's absolutely necessary. And it's not just AI technology. I was also talking to my colleagues working in, say, neuroscience and computational psychiatry. So applications of AI there can literally help you read people's mind from their text and speech and video and so on. And that's kind of not that terribly hard to do. And it's already happening. So even there, similar kind of questions about like neuroethical AI and so on and so forth. So I think it's going to be becoming more and more of a problem. So I think there should be really a much better dialogue between AI people and government.
I think that Europe might offer like a nice perspective on that, because of the EU, like the banding together of many European countries and making laws like GDPR together, which was completely absent, well, I guess still is to some degree in North America. And in particular, Denmark is like we have someone from Denmark is kind of the bane of the big data giants. So this is the EU competition commissioner, who is Margrethe Vestager, and is always suing Google and always suing Microsoft for something, for many billions. So I think that countries like Europe have figured out, how to band together in order to protect people, and make data to some extent be ethically harvested from people. But there are, of course, countries from other areas of the world that don't have this protection yet, that can't make the same ethical demands by themselves without risking, losing out on something. I think, in terms of like investment and like, just getting the brains to do AI, like a little country like Denmark, where the economy is really all about like making a bunch of academics, this of course is something that is a priority, but the investment in Europe compared to what's happening in Canada and obviously the US and China there's no comparison. Like the investment blows Europe out of the water in AI. So I think in terms of competition, we'll see how it goes. Maybe there'll be more investment.
Right. And I think, yeah, that's also an interesting dynamic, right? Because the level of investments will also create some of those asymmetries. And ultimately, I think, depends on how the governments, as Irina was saying, having that interaction with governments is going to be essential in steering some of the investments, but also the direction that research takes and ultimately implementation of that research.
Yeah, I just want to apologize to all the economists for talking about stuff I don't know about. I talked about it the best way I could.
So hopefully we will have economists on the call that you're able to offend, because then that would make for an interdisciplinary conference. Very cool. So I'm going to ask one last question, and then we'll take some from the audience. I've already seen there are a couple there that we'll touch upon. So this is an interesting one, and I'd love for Zach to take a crack at it, and then we'll have Irina and Natalie chime in as well. It's a really short question, but I think there's some interesting things to unpack there. How do you make a model explainable if it is not interpretable?
Sure. I think my general feeling on the discourse about a lot of these kinds of questions about interpretability or explainability is we usually put the cart before the horse. So like we have a certain kind of frames of types of statements we like to make. How could it be X if it's not Y? What's the trade-off between interpretability and accuracy? What's the trade-off between explainability and accuracy? And people want to just jump right into debating it because it's like it fits the I don't know, it looks like a Reddit thread or something. It has the feeling of a proposition about which people would want to have opinions. I think the problem is that these propositions are not well defined because they're expressed in terms of terms that people haven't really articulated. So the terms interpretability and explainability, depending on what paper you're reading, may have no definition at all, may have a sort of contextual definition, which is in which they are used interchangeably, may have a contextual definition in which they are used in very different ways. There are certain things that when I kind of first encountered that area, my first thing that I tried to do is say, we need to take a step back and like this really invites something that looks more like analytic philosophy than something that looks like machine learning research. We need to figure out what are the concepts people are talking about, what's the right category of concerns. There is a little bit of a distinction, in my first attempt. So my first attempt was just I wrote a more of a position piece called The Mythos of Model Interpretability, where I tried to sort of unpack what are the things people are talking about in these papers, not maybe to presuppose what they should be talking about, but to sort of figure out what is the spectrum of meanings people are maybe hinting at, and what is the spectrum of problems people are trying to work on, and how are these things, if at all, related to each other. There are certain distinctions, like sometimes people are referring to, like one way of interpreting this interpretability versus explainability is that there's a category of research that sort of makes statements about what is the form that a model must take, and others that are sort of saying, you give me a model, I'll give you a procedure, a post hoc procedure that gives you some kind of insight into how the model works. The problem is that most of these procedures are or even most of these like model requirements are sort of just defined like by fiat, not like here's what it gives you. Like, if you look at these things like saliency maps, concept activation things, integrated gradients, LIME, all these models, they're sort of defined procedurally. Like we do this and then we sample from points there and then we fit a model and then we do this. What is it actually telling you is not so clear. So, you know, like through that distinction, you know, sure, you can have a model that on which you could apply one of these post hoc procedures, but doesn't comply with some kind of assumption about how the model is structured. But I think the bigger question is to step back and actually think, what is it that we're after in the first place and why? And how do these properties relate to it? And so if you read papers talking about interpretability, they make a lot of kind of, you read the introductions, they're really swinging for the fences. You know, we talk about contestability, and we talk about decisions in criminal justice. We talk about doing basic science. We talk about causality. People talk about robustness. It's really unclear on a technical level what people are providing in these papers relates to any of those underlying desiderata. You know, inferring causal effects is hard, but there's a mature discipline around, you know, what assumptions are required and when can you do it. And what people kind of want to do is sort of, I think very often these terms are arising in the context of a literature where people want to make a claim of having addressed something, but don't want to necessarily like deal with the fraught technical problems of, like, if you say you're working on causality, then your paper is going to be reviewed by the causal inference people, and it's going to be clear that you haven't identified a causal effect and don't necessarily have the right observational data to make the kind of statement you want. But if you just train a supervised learning model and then say we use this technique and this explainer and this explainer and whatever, and then we get these insights, it's, you know, you're sort of like, the field is almost by definition sitting in that space where it's impervious to attack because it hasn't defined anything concretely enough to enable, you know, that kind of discussion. So, I mean, that's, you know, maybe I'll just leave it there.
Yeah. Irina, Natalie, you wanna? Yeah, Irina.
Well, yeah, I guess, yeah, that kind of described all various issues with and challenges. Well, of course, those notions are indeed not well defined, but more generally, intelligence is not well defined either. And quite a few other notions in machine learning are not well defined. So the largest difference between machine learning and mathematics is that most of things are defined in natural language. Well, which is plus and minus because it's more expressive, but it's less precise. But indeed, there are various kind of notions of interpretability, and like in biology, like neuroscience and so on in sciences. Indeed, by interpretability, people often meant at least being able to pinpoint which input variables were kind of most involved, most kind of responsible for obtaining your result, if you're talking, for example, about prediction. And perhaps you might not be able to have like other types of interpretability, but you can at least aim to get something like that. So I don't know, again, they might be not even causal, but at least it's some notion of selecting subset of important factors that affected decision of the system. You might not be also able to explain how the decision was made, but at least you might be able to pinpoint what affected it. So I think at least something along those lines could be useful. But again, it's very, very limited notion of interpretability. And yeah, well, also from my experience using, say, deep learning in brain imaging, that's of course was always a challenge. It's much easier to use models that are kind of by design are interpretable, like use something like sparse graphical models or sparse regression, and you see what matters, and then you can map it back to brain and explain. If you run some, I don't know, recurrent convnet on your data and it does much better than previous methods in detecting some mental states, like what did you learn from that? Well, again, there are various methods. People try to map features of deep nets back to the input, basically all kind of deconvolutions and you name it. And again, it might show you back in your input space what mattered, what was important. So it's at least one type of, I guess, interpretability you can try to achieve, but you might not be able to fully explain how decisions are made.
Yeah, Natalie?
Yeah, so I think there's like this, a sort of like absence of the notion of what goes into these models. So there's first what goes into these models, and then there's like, you know, the mechanics of the models and what is the capacity inside of them. And like on the one hand, I think you can do some studies on like the set of different potential models and prove that there is a capacity to perform, you know, some task, right? But at the same time, like I think, you know, like we shouldn't be putting data about you know, white and purple elephants into the model and expecting there to come out diamond rings. Like we have to be quite intentional, like and think, you know, intentionally about what we are doing with these models, and in being more intentional when we're doing our experiments, and in trying to predict like how all of the possible ways that the models can like interact with the data, that we should be able to you know, do some explainability analysis in that way. And in that sense, I think, you know, that could also be something that is not just for computer scientists then, because we're not just dealing with a bunch of numbers, we're actually also dealing with different nuances of what's going into these models.
Yeah, no, that's definitely something to think about. And I think, you know, ultimately it boils down to, I think, you know, just at least giving it some consideration at the very least, and engaging with others who have done some work in this space, who have given it a lot of thought. And, you know, I mean, I think all of you alluded to the fact that, you know, there is vagueness rather in a lot of these definitions, yet there is still value ultimately that, you know, comes out of it. I think it's, you know, to borrow from Zach's phrase, you know, defining that category of concern, right? I think will help to clarify those discussions. I know we're pulling up to the end of time that we have together here, so I will take one of the questions that was here, and let's see if we get enough time to get through to some of the others. So I'll quickly read it out for you guys. So Robin posted that they attended a talk at SIGKDD, and there was a lot of talk about how to maximize clicks with recommenders, but nothing about the second order effects, like how YouTube recommenders can lead users to radical content. So how do we get those second order effects on society to be first order concerns for practitioners?
Anybody else want to jump in here? Or
Yeah.
I'm from New York, so if, like in the worst case scenario, if you need somebody with an opinion, you know, New Yorkers will oblige. So this is a hard question. My work, some of my work, and a current project right now with my PhD student, Lechi Liu, is addressing this sort of very concern. So we tend to basically just deal with the quantities that are observable in the sort of like harvested offline data, because, you know, not just because we're crazy or stupid or whatever, but because like there's a reason, which is that these things are like objective, and we can get everyone to agree about them. They're the wrong quantity, but then we could objectively assess it how well we predict the wrong quantity. And so, you know, all these other things, you know, it's like if you have you can turn around this kind of research fast, because you don't need a wet lab experiment. You don't need human in the loop experiments. You don't have to go out and probe the world and see how it reacts. And so there's a reason why most research centers on it, which is that if you're smart and you're a good engineer and you know how to do some, you know how to do a little bit of the right kind of math, you can turn out an endless stream of papers at a fairly fast clip, like in this kind of first order sort of analysis of just, I've got logged click stream data, I want to predict stuff. Now you can go just a little bit deeper, specifically in the recommender systems literature. You could look at research by people I guess a good starting point for this research would be stuff like maybe on the order of like 4 or 5 years ago, the papers by Adith Swaminathan and Thorsten at Cornell. Adith is now at MSR, is a really wonderful researcher working in these areas. He starts thinking about, well, you have various kinds of exposure bias. You recommend people think they're more likely to see them. You have like different propensities of seeing different items, and what you actually observe is like, given that someone clicked on, given that something was exposed to someone, it's like someone, there's an exposure model compounded with like a reaction model. If you don't account for these propensity scores, then you could have all kinds of feedback loops and start thinking about how do you do the right kinds of corrections, and you have all kinds of clean sort of like things that look a little bit like inverse propensity weighting and causal inference. Then you have the kind of deeper thing, which is like not just looking at, directly this kind of, idealized model of exposure, but actually considering like the dynamics of how humans are interacting with systems and how the recommender systems are actually altering their preferences, not just changing the set of exposures. And that, now suddenly you start entering a territory where on one hand, this is the real problem. Like this is the important problem. You're concerned with like YouTube rabbit hole type dynamics of like someone starts off listening to talks by like some slightly heterodox like individuals, and then immediately after they start getting recommended things by people who are kind of more like alt-right type content or alt-light type content, let's say, and then they start getting recommended, hardcore alt-right content. This kind of like radicalization dynamics where it's not just like correcting for a set of exposures and feedback loops, but you're really concerned with the ways that the recommendations are actually influencing the dynamics of behavior itself and people's beliefs and preferences. On one hand, that is maybe in some sense the most important problem societally, but it's also the one that we have to, be humble about our power to understand these things. Like we can't just construct a toy experiment and say, like, we can construct this toy experiment to give qualitative insights, but not to like really tell us how the system works. And if we don't understand how the system works, then I think we really need to step back and think, well, what is like the cautious, if we're going to be humble, if we're going to have some sort of humility about our ability to understand these systems, what is the way to act cautiously? What is the right kind of safe behavior? And I think it's not always the same as the profit maximizing behavior. So for example, I think in a lot of places, there's a good argument that like, the standard just chronological feed of you see what people shared, people who you followed shared in the order that they shared it. That's it. In some ways, this is a little bit of a more robust system, I think. And once we make this decision that we're going to go out and we're going to start implementing systems that can have kind of like arbitrary behavior and upweight content by amounts that we don't have control over, we open ourselves up to the possibility that it won't, that it will be content we deem to be problematic.
Maybe I just quickly add that like this type of like network and recommendations, like these dynamics have been studied for like a really long time in sociology, so I think still again, like interdisciplinary studies, like this recommendation problem is everywhere. I mean, for us academics, citation is one of them, these are everywhere. So interdisciplinary teams together.
Perhaps just as it was suggested earlier about figuring out better policies and studying kind of dynamics of interactions, same thing here, well, simulations. And perhaps in terms of, well, it might be a little bit tangential, but with social dynamics on social networks and how it's also affected by recommendations, it almost kind of makes you wonder, like, if you don't like the potential kind of dynamics you start observing, and it seemed to be, well, not robust in some sense, I don't know, or it kind of seemed to go in the wrong direction. So perhaps you can also implement as well automated interventions. Like you can use, well, it's not exactly recommendations territory, but for example, bots they can be used both for good and for evil. And that's if they're being used for evil, then maybe you need to consciously start implementing those that will counteract the actions of bots trying to bias opinion of population in certain directions. So you need to kind of have if there is an army, you need to have your own army to fight that. So basically, whether it's, I don't know, propagation of fake news or biasing opinions in certain particular directions and so on and so forth. So basically, if there is kind of cyber war going on, then you better take actions.
Right. Well, I mean, I think this has been a fascinating discussion, and I'm just taking a look at the time. We're at the top of the hour, well, at least in Eastern time, depending on where you're joining us from today. You know, we can keep talking for hours and hours. I think there's so many fascinating things to talk about. We've just scratched the surface, and my apologies to some of the audience members who asked questions, and we did not get a chance to get to them. Well, I guess, you know, please feel free to continue to have these conversations offline as well, because I think they're very, very important points of discussion. But really a huge thank you to Natalie, Irina, Zach for taking time out of their very, very busy schedules to speak with us. It's been fascinating. I learned a ton, and I hope everybody else did as well. Thank you to the organizers as well for considering bias, fairness, and ethics as an integral part of the conference, for making it a core part of the discussions today. And yeah, well, thank you to all the folks, the attendees who have been with us since the morning for this very lovely conference. We will be starting very, very shortly with the poster spotlights on supervised and deep learning. That's right up on the program after. But if there's anything else from the organizers, I'll leave it up to them to chime in. But again, a huge thank you to our panelists for taking the time today. Had such a great time. Thank you so much.
Thanks, Abhishek, for having us.
Thank you. Thanks for inviting us.
And thanks to the organizers.
Thank you.
Bye, everyone.
Bye. Bye-bye.
I hope everyone enjoyed this great panel that we just have. It's time for our third spotlight session, which will focus on supervised and deep learning research. Once again, we just have 1 minute per spotlight. If you find anything interesting, please come to the poster session at 3 p.m. in Galatown to hear more about it.
Hello, everyone. My name is Soroush. I'm a PhD candidate at Concordia University. The topic of the work I'm presenting here is using artificial intelligence to discriminate two neurological disorders that are named Parkinson's disease and essential tremor. The reason we have selected this topic is that these two specific disorders share very similar and overlapping features, and the diagnosis rate even for neurologists is not that high. It's about 80%, and it's a challenging task for neurologists. So to tackle this problem, we have recorded the dynamics of hand motion for a large population of patients. And then we have used convolutional neural networks to process the raw recordings and then extract some features. And then at the end, we have used a QDA classifier to process the features. So we were able to achieve 95% of accuracy, which is much higher than the state of the art. And our work is called NeuroDNet. Thank you so much.
Hi, I'm presenting our work, Guide and Attention for Fine-Grained and Hierarchical Classification. We're a team of 6 authors from Paris, Centrale Supélec Paris, Paris-Saclay University, Mila, and MIT. Insects are vital for environment, but they disappear at an alarming speed, 80% fewer insects in 25 years. Our technology of classification is part of a virtuous cycle involving citizens and their smartphones. We built a network in order to classify those butterflies. We got 87% in accuracy, top 3. Then we use GradCam visualization tool using reverse gradient descent in order to see that our network was more focusing on background instead of the butterfly. As a prior, we decided to use a segmentation and then to add an additional loss in order to penalize features outside the masks. We enhance our result. Sum up is here.
Learning on complex domains requires high volumes of data, yet these are not always available. Conversely, machine-readable expert knowledge exists that could complement the datasets. To guide the learning and make up for data scarceness, we use knowledge graph patterns over a domain ontology as extra descriptive features. The core idea is those patterns reveal the shared conceptual structure that is otherwise invisible in raw data. By bringing in the abstract vocabulary from the ontology, they go beyond matching labels and distancing numbers. Moreover, the graph structure provides context to pattern elements. Yet, they are challenging to extract as basic operations pertain to subgraph isomorphism enhanced by ontological relationships, e.g. class membership. The approach is currently applied to dairy production data. An increase in predictive power due to the injected expert knowledge and faster model convergence are among the expected benefits. Also, explainability should be enhanced due to links from features to ontological entities.
Continual learning is the problem of learning from a non-stationary stream of data composed of sequential tasks, such that the learned model should perform well on newly learned tasks without degrading performance on the old ones. We adapt the OML objective so that it is optimized online by the model parameters using model-agnostic meta-learning or MAML. A small replay buffer is also populated by reservoir sampling on the data seen during training. We use a MAML update where samples from the new task are used to take multiple inner loop gradient steps and are then interleaved with samples from the replay buffer to compute the meta loss. In this way, we use the OML objective to learn new tasks while maintaining performance on old ones. We introduce a set of per parameter learning rates, or LRs, to be used in the inner loop of the meta updates. We propose updating the weights and LRs in the meta update asynchronously so that we first update the LRs and then use them as the learning rates for the meta weight update. Our experiments involve learning a sequence of visual classification tasks on the MNIST CFAR100 and TinyImageNet continual learning benchmarks in task-agnostic and task-aware conditions. We define several ablations to capture the gains from the online objective, our LR modulation, and the async update. We see superior performance of our ablations, with LaMAML performing the best amongst them. In conclusion, we propose a fully online algorithm for continual meta-learning with inbuilt learning rate modulation.
Hi, this is Yassine Yacobi, and I would like to present to you today our paper entitled Structured Convolutional Kernel Networks for Airline Crew Scheduling. As the title suggests, we are interested in a particular problem of airline crew scheduling called the crew pairing problem, where we search for a minimum cost set of anonymous feasible pairings, ensuring all flights are covered and all airline regulations are met. The currently available solution uses CNNs to produce flight connection probabilities to alongside the solver, but this approach often fails to produce feasible initial solutions because we don't incorporate constraints on the output. To bypass this limitation, we propose a new predictor called struct-CKN, combining convolutional kernel networks and structured prediction framework. First, we sanity check our approach on the OCR dataset, then we use the flight connection dataset modeled as a general CRF to warm-set the crew pairing solver. By doing so, we reduce the solution cost by 70% and the cost of global constraints by 97%. Thank you for your attention. For more details, please contact me during the poster session or at yassineyacobi@outlook.com.
The main research question in this paper is that how to differentiating out of distribution set for selecting the most effective one for training a well-calibrated CNN which can detect many unseen out of distribution sets. The proposed protection level is able to characterize out of distribution set. We propose three metrics for measuring the protection level. One is softmax-based entropy, which is measuring how uniformly the out-of-distribution sample are distributed to the in-distribution submanifold. The second metric is coverage ratio, which means that how much the submanifold are covered by the distributed out-of-distribution sample. And the third measure is coverage distance, which is measuring the average distance between the out-of-distribution set and the submanifold. We assess our metrics on several data sets, and we finding the most protective out-of-distribution set for each in-distribution set and the least protective out-of-distribution set for each of the in-distribution set. And we finally showing that if training an augmented CNN on a most protective out-of-distribution set, we can have a higher detection rate of unseen out-of-distribution set, while training an augmented CNN on least protective out-of-distribution set doesn't lead to the CNN with high detection rate of unseen out-of-distribution set. Thank you.
Recent work claims that adversarial training is needed to perform image synthesis with a deep classifier. In our experiment, we didn't find a strong correlation between robustness accuracy and qualitative result on image synthesis test. We present the hypothesis that what we really need is smoothness of the input gradient field, and that adversarial training is only one way to achieve that. We develop a new method to enforce the smoothness by sampling a random label for each example. We compute the input gradient for this specific random label to generate a new example in order to train the classifier. Here are some image-to-image translation results with our method.
In the current COVID-19 pandemic, some countries have been overwhelmed and forced to implement triage protocols to ensure that critical resources like ventilators are given to those with the highest chance of survival. In this work, we attempt to provide accurate quantitative information to help make this decision by applying deep learning to chest X-rays. We first trained a dense net on a large-scale non-COVID-19 chest X-ray dataset to predict radiological signs of disease. We used this dense net to extract features from a COVID-19 dataset collected in 3 Quebec hospitals and train classifiers to predict the outcome of mechanical ventilation. Convolutional features reach a 0.77 AUC at predicting the outcome in leave patient out cross-validation. When combining the convolutional features with the known risk factors, we obtain a 0.96 AUC, higher than only the risk factors. After further testing, we hope that this model can be incorporated in the Health Ministry triage guidelines.
Hello, I'm Anirudh. Today I'll be presenting our work on dream recall classification. Our brains are still a mystery. Sleep and dreams are one of the most puzzling questions in brain research. Here we try to understand why some of us recall dreams more frequently while some others don't. And we try to do using deep learning approaches without any prior feature selection. EEG data of 36 participants was used. The data was divided into 5-second segments and passed as an image to the CNN model. The CNN model developed had an architecture as shown, divided into feature extractor and a classifier. Our model achieved significant decoding accuracies up to 75%. T-SNE embeddings were calculated using feature extractor outputs and plotted to see if there were any subject-specific clusters. It was found that our model does not fit to subjects. To understand what brain features were used by the CNN model, we developed a pipeline using guided backpropagation and FOOF to get the brain topomaps. The features obtained were found in line with the previous literature and also led to identification of new features. In this work, we show how deep learning can be used to advance our understanding of brain mechanisms underlying dream recall, at the same time develop a generalized pipeline to visualize important brain features. Thank you.
Hi everyone, we are looking into graph convolutional networks, short GCNs, and propose a network that alleviates one of the major issues of GCN-based methods. We are doing semi-supervised node classification, where we want to classify missing node labels of a weighted graph while having access to a set of node features. GCN layers suffer from oversmoothing because they are based on the low-pass filtering operation. Based on this observation, we introduce a hybrid architecture complementing GCN filters with bandpass filters constructed via geometric scattering, as you can see in this image. The method achieves very good results overall, and performance across different datasets suggests that it indeed alleviates oversmoothing. If you want to know more, feel free to join us during the poster session. Thank you for your attention, and I hope you're having a great day.
Hi, my name is Mito. This is joint work with my collaborators Nicolas Balas, Luis Castrejón, and Mike Rabat. In this talk, we try to improve the computational efficiency of contrastive semi-supervised learning of visual representations. The state-of-the-art approach for these methods is this approach called SimClear, and a standard approach in the literature is to conduct self-supervised pre-training followed by supervised fine-tuning. So for example, in the SimClear method, they first try to maximize the agreement between representations of the same image but under different data augmentations. After this self-supervised pre-training phase, they fine-tune the encoder using available labels and a standard cross-entropy loss. While these methods are data efficient, they require at least an order of magnitude more compute than standard supervised learning with a cross-entropy loss. And so what we propose here is to use these available labels directly during the pre-training phase to reduce the computational overhead of our method. We propose a supervised noise contrastive estimation loss called sunset. There, the idea is to maximize the agreement between representations of different images, but from the same class. And by optimizing this supervised and self-supervised loss directly during pre-training, the hope is that we can improve the computational efficiency of our method. We conduct experiments on ImageNet with 10% of the data labeled. There we can actually save up to 62% of the compute of these state-of-the-art methods by using these available labels during pre-training using our proposed approach. Just for context, that's about 39,000 petaflops. We can also surpass the state-of-the-art accuracy by 1.2% top one while using 47% less compute. We also evaluate downstream transfer and the results look great. Please check out our paper if you're interested.
Hi, welcome to the teaser of our paper, Evaluating Logical Generalization in Graph Neural Networks. This is a joint work with Shagun Sudhani, Joel Pinu, and William L. Hamilton. So in this work, we release a data set known as GraphLog. So this data set is a collection of multiple knowledge graphs built using first-order logic, and the task is relation prediction. So by using this multiple knowledge graphs, you would use a graph neural network to solve the particular relation given a source and a sink node. So we have multiple worlds, and these worlds are built using first-order rules, and you can divide these worlds, and then you can get a collection of graphs for all of these worlds. This nice setup helps us to evaluate graph neural networks in meta-learning, multitask learning, as well as continual learning setups with explicit inspection of your graphs, how it is working. So we provide our code in pip install GraphLog, and this is a nice API which lets you play with the dataset, as well as we provide data loaders and visualization scripts. Thank you for listening to our teaser. Please come by to our poster if you have more questions.
Hi, we are from Laval University and we are presenting our paper called Template-Based Unseen Instance Detection. Much of the focus in the object detection literature has been on the problem of identifying the bounding box of a particular class of object in an image. Yet, in different contexts, it is often necessary to find a specific object instance and be able to do so with little to no training time. In this context, we propose a generic approach to detect unseen instances based on templates rendered from a textured 3D model. To this effect, we introduce a network architecture which employs tunable filters, and leverage learned feature embeddings to correlate object templates and query images. At test time, our approach is able to successfully detect a previously unseen object, even under significant occlusion. Finally, our method surpasses previous template matching methods in occlusion settings and is on par with approaches trained on the test objects.
Hi, my name is Elliot Lane. I'm a grad student in Dr. Blanchette's lab at McGill University, and I'm presenting some of my recent work on supervised learning on phylogenetically distributed data. This work was motivated by the observation that data sets comprised of multiple species can often violate the IIT assumption. Genetic features may be distributed differently between species that are closely related and those that are further away on the phylogenetic tree. To address this issue, we developed the DendroNet training method. Rather than training a single predictor, DendroNet instantiates a family of predictors related by a tree with the same topological structure as the phylogenetic tree relating all training samples. These predictors are trained simultaneously, each fitting the data in its respective subtree. Tree-based regularization ensures that closely related predictors share similar parameter values. DendroNet outperformed all comparison methods on two tasks of interest: the prediction of antibiotic resistance in bacteria and a fleeting lifestyle in fungi. There are more details available on our poster, so please feel free to check it out.
Accurate area measures of surface water habitat is essential to determine a whale population size. This means excluding land and survey images, which is not whale habitat. Currently, analysts do this detection by hand from photographs because the automated solution isn't as simple as blue equals water, brown equals land. Previous attempts to automate this task all yielded inaccurate information for our needs. Murky brown water, clear water with deeply submerged rocks, and inland lakes all confounded the results.
Although deep learning can be used for this task, common drawbacks include having to tile the enormous aerial images, which is computationally expensive, and expecting pixel-level segmentation of ground coverage as labels, which usually doesn't exist. Since saliency methods like GradCam can leverage global labels for segmenting, made easier by rescaling the whole image to thumbnail size, we can try and overcome both of these limitations. The results showed this is a promising approach given several different model architectures. Future work will add more data, investigate the best saliency method to use, and look at varying the level of fine-tuning and post-processing.
Patch-up, a regularization technique for convolutional neural networks. Some of the state-of-the-art approaches have some weaknesses. Manifold intrusion is one of them, which happens in the mix-up approach, where you're trying to mix two samples and their linear interpolation isn't always aligned with the related target. A similar problem happens in the cut-mix approach, where the candidate blocks might not be correlated with the label. To overcome these issues, we introduce patch-up, where we randomly select layer K, then we compute hidden representation of two samples, and we denote them x1 and x2, apply patch-up binary mask on these two feature maps. Then we can either apply hard patch-up or soft patch-up, where in hard patch-up we're swapping those patches, and in soft patch-up we're mixing those patches. And then we continue with our forward propagation. This allows us to explore more subspace features. Our loss function will look like the following, which has two main components. The first component is trying to teach the model to distinguish where there is no change and where there is a swap or mix. The second component is trying to teach the model to predict the correct related target. We performed our approach on 3 different models with 3 different data sets and outperformed state-of-the-art approaches, sometimes by a large margin. The tasks were image classification, generalization on deformed images, robustness to adversarial examples, in which case we used FGSM attack, and then we were also able to produce a wider variety of features. For more information, visit our poster. Thank you very much.
I would like to present our work, Active Learning, Unified and Principled Method for Query and Training. In this paper, we propose a unified and principled approach for both query and training and the deep active learning problem. More concretely, in the query, we propose an explicit strategy with uncertain and diverse criteria. As for the training procedure, we propose an algorithm which utilizes the labeled information and also leverage the unlabeled information to promote prediction performance. Our empirical results indicate its benefits. For more information, I would like to invite you to check our paper and code.
CNNs are one of the most successful learning architectures. However, their performance drops when they are trained using a small number of samples. Unfortunately, many real-world applications do not have access to large datasets because of data scarcity. By using rat-brain data as the initial training dataset, sizable gains were obtained after transfer learning for our small clinical datasets, compared to CNNs from scratch. However, transfer learning was not powerful enough as in cases of data heterogeneity or low resolution. What we propose to improve the classification is a cumulative learning approach, which consists in training the same model through several classification tasks over various small datasets. Our methodology goes beyond transferring a representation learned on one dataset to another, since it accumulated mass spectrometry knowledge in the final model without any loss of generalization, which suggests that a generic representation of mass spectrometry classification problems might exist.
We present lens design generation with a deep neural network. Having a good starting point is mandatory for any lens design optimization process. Using deep learning, we created an app that infers a selection of high-quality lens design starting points tailored to the desired specifications. Under the hood, we use a deep neural network that takes as input the half-field of view and entrance pupil diameter and outputs the surface curvatures, thicknesses, and glass variables required to model the lens design. Using an RNN as a backbone, our DNN model learns a shared representation for different lens structures. To train the model, we combine two training objectives. With supervised training, the model learns to replicate scarce reference designs from the literature. With unsupervised training, differentiable optical ray tracing is used to generalize to a wider variety of specifications. We also show that our inferred designs compare favorably to reference designs. For more information, come see our poster.
As we all know, the current outbreak of COVID-19 is putting unprecedented stress on the healthcare system. In this work, we attempt to track and predict COVID-19 progression using deep learning on chest X-rays. We first train a dense net on a large-scale non-COVID-19 chest X-ray dataset to detect 9 radiological signs of disease. We show that, when applied to COVID-19 X-rays, there are significant differences in radiological signs between recovering and worsening patients. Furthermore, convolutional features from the dense net can predict disease progression with an 83% accuracy. We hope that this work can eventually be used in hospitals to proactive intervention on at-risk patients with further testing and validation.
Hi, my name is Frederic, and today I'll present Bayesian active learning for production. This is joint work with Parmida and Alexandre. While active learning is a dynamic field, current benchmarks do not highlight issues found in real datasets. Also, current active learning techniques are too slow and expensive to run in production. In this paper, we show that active learning is robust to class imbalance, annotation error, and model convergence. Also, we make active learning faster by performing partial uncertainty sampling, which accelerates the process by 3 times. Finally, we propose our Bayesian active learning library, which accelerates the transition from research to production. We propose state-of-the-art methods, such as MC Dropout, BALD, and more. Our library is also a member of the PyTorch ecosystem for its outstanding documentation. For more information, please come to our poster session, and thank you.
Hi everyone. Our last spotlight session will focus on computer vision and natural language processing. If you found anything interesting, please come back to the poster session at 3 p.m. in Gather Town to hear more about it.
The forest industry continuously wants to increase its productivity. However, operators are currently overloaded by tasks they must perform, limiting the efficiency of their machine. Therefore, a new technology imposes itself. My name is Vincent Grondin, PhD candidate in computer science at Université Laval. This past year, under the supervision of Dr. Philippe Giguère, we focused on how deep learning techniques can be employed to automate harvesters' operation. In doing so, I developed a forest environment simulator, generated a synthetic dataset, and trained an object detection model to automatically predict grasping location on trees. Being the first effort to employ deep learning techniques on harvesters' operation, we remain unsure about how they will perform in the harsh forest conditions. Nonetheless, we address some of these uncertainties by predicting the grasping location on trees with synthetic images. Thank you.
This work focuses on the detection of local anomalies in videos. As you can see in these clips, local anomalies are independent from other surrounding activities. Therefore, we use a pre-trained object detector for extracting the bounding box locations, which are projected to the previous frame for extracting the spatial gradients. Our goal is to have a framework which makes very bad predictions for abnormal locations. We do this by first training two generators which learns to map normal spatial gradients and appearances in an adversarial manner. We then apply them to produce partial reconstruction errors with which we adversarially train a discriminator. During testing, we directly use this to predict the likelihood of a region being abnormal. Here we show a short demo of our method, which we evaluated on several public datasets. The results show that our method is better or competitive with the state-of-the-art. For more details, please join the interactive poster session. Thank you.
In this work, we study the representations learned by neural networks that are trained to track objects in video. In the single object tracking setting, the network is given a bounding box around the object of interest at the start of the video sequence. The network must learn to output the bounding box corresponding to the same object for every remaining frame in the video sequence. Two images are input to the network at every time step. The search crop is usually extracted around the previous location of the object found at frame t-1. This exploits the principle that objects move smoothly in videos and limits false positive detection. As a consequence, objects are often centered in the search crop. The network learns to exploit this, which leads it to detect the most salient objects closest to the center of the search image. This strategy ignores the appearance of objects. Here we see that despite inputting different images into the object branch of the network still tracks the most salient object closest to the center of the image. We add an auxiliary detection task to avoid this degenerate solution and encourages more discriminative target representations. We study the final tracking strategy learned by the network using perturbation analysis. We find that the representations learned using our approach not only performs better, but also encourages the network to learn more discriminative representations of object appearance.
In the object detection task, merging various datasets from similar contexts but with different set of objects of interest is an expensive way for crafting a large-scale dataset covering a wide range of objects. However, a merged dataset contains many missing label instances causes a drop in performance of object detector. With the goal of training one integrated, robust object detector with high generalization performance, we propose a training framework to overcome the missing label challenge of the merged dataset. More specifically, we propose a computationally efficient, self-supervised framework to create on-the-fly pseudo-label for the unlabeled positive instance in the merged dataset in order to train the object detector jointly on the grand truths and pseudo-labels. We invite you to read our paper at the available link here. Thank you.
Hello everyone. My name is Sébastien Leblois. I'm a PhD student at Laval University in Quebec City. I'm the main author of the paper Input Dropout for Spatially Aligned Modalities, which was written during my master's degree, also at Laval University. The question we want to answer in our article is how can we use additional modalities only available during training to augment the performance of deep learning models on computer vision tasks. Previous methods were proposed, but they are not versatile and usually need multiple networks. We propose a simple and flexible training methodology to take advantage of these additional modalities available in dataset even if they're not available at this time. We call this technique input dropout. According to our results, input dropout is an easy yet very effective way to use more modality in training than in testing. Thank you.
Hey everyone, my name is Marta, and today I'm going to tell you about a collaboration we've been working on at Mila and the Montréal Insectarium in order to improve butterfly image classification using spatiotemporal features. So we can use machine learning to automate the labeling of butterfly images, but it's still a challenging task. For example, here I'm showing you two species of the genus Sphaeria. And while they might look similar, they live in different parts of North America, so it would be a lot easier to differentiate them if we knew where the images were taken. This leads us to our research investigation. We wanted to know if we could use where and when the image was taken in order to improve our butterfly image classifier. So we trained two encoder models, one that predicts the species from the image and one that predicts the species from spatiotemporal features. At test time, we're able to use our spatiotemporal model as a Bayesian prior and multiply the probabilities from the image and spatiotemporal models to get our final prediction. When we incorporated where and when the image was taken, we saw improvements of up to 5% compared to using the images on their own.
We present RGBDE event camera calibration for fast 6DOF object tracking, the first 6DOF object tracker using an event-based camera. We combine our event-based sensor with the RGBD sensor. Both sensors are calibrated temporally and spatially to capture 10 RGBDE sequences. All sequences are labeled with the object 6DOF position by using ICP. We use two networks in cascade to compute the final prediction. First, our network computes a coarse estimate of the pose given only event information. And second, we use a state-of-the-art RGBD tracker to refine the final pose. As the RGBD network is limited by frame information only, we show that event information between frames make the framework much more robust to large displacement. In all our sequences, tracking failures are reduced by more than 60%. For more information, refer to our paper.
Hi, my name is Anthony Birdel. I'm a PhD student in the lab of Flavie Labo-Cardinal and Audrey Durand. I will be presenting a weakly supervised learning architecture, which we termed WIS, that uses solely all-image binary labels as training examples. WIS is a fully convolutional architecture followed by a linear layer that tries to predict the content of an image. At inference, we obtain information from the network using gradient class activation maps and obtain a feature map that is thresholded to obtain the segmentation of structures. We compared WIS with the weakly in a fully supervised unit architecture and showed similar or increased segmentation and detection performance. We used a dataset of large electron microscopy images to detect extremely sparse structures in the field of view to assist the experts in their labeling task. As a whole, we show how WIS can help reduce the burden of the generation to training set while maintaining the segmentation and detection performance, which are comparable to fully supervised techniques.
Hello, we will explain today how we forecast hurricanes using computer vision and language models architectures. Predicting hurricanes accurately is a critical task to protect people and properties in due time. We also aim at advancing machine learning knowledge in its ability to predict chaotic systems, and we want to pioneer hurricane forecasting using state-of-the-art language models architectures. Our data comprises 3,000 hurricanes, and we have tabular and vision data that we have to mix efficiently.
To mix tabular and vision data, we use the following architecture. The images are transformed by a CNN and fed together with tabular data to a GRU. The results we obtain are promising, and the best models surpass the accuracies of a naive baseline that considers predicting the same intensity in the future or XGBoost model. That urges us to focus our work on sequence-to-sequence tasks, attention mechanism, and multimodal learning. That work was conducted by Léonard Boussiou, Théo Guénet, Cynthia Zhang, and Professor Dimitris Bertimas. Thank you.
Hello everyone, my presentation is about the effect of bad weather on computer vision algorithms. We all know that bad weather affects most of them, but we do not know how much it does. What if we had a knob that let us add any level of rain to an image? First we could add wetness, and then a bit of rain, a bit more, and a lot more. Augmented image like this would enable us to quantify the impact of rain in a systematic fashion. We propose a method that combines two different ways to add rain to an image. First, we have this physics-based rain rendering technique where we simulate rain particles in a scene for a rainfall rate. Second, we generate this wet backdrop by using an image-to-image translation approach. This combined rain rendering method makes possible the augmentation of a whole dataset for different rainfall rates. With it, it is now possible to analyze the effect of rain at various fall rates on object detection, semantic segmentation, and depth estimation. Also, we can use this image to fine-tune models to improve the robustness to rain. See our poster or paper for more details.
Inspection of Hydro-Quebec's power lines and substations is expensive and dangerous. By using AI-based object detection models, this project adds autonomous inspection capabilities to our fleet of robots. A novel power line inspection robot is the first deployment target. To build the dataset, we extract images from videos recorded by the robot. However, few such videos are available. To compensate, we generate synthetic images for training by randomly assembling CAD models of components. While adapting our models for this task, we observe that performance is poor with respect to certain video feeds. We use saliency maps to determine improvements to the dataset. We then expand our training dataset with real images augmented by a series of transformations. Finally, we validate with real data while k-folding across source video feeds to enforce independence. Our best result is obtained by first training with our synthetic dataset and then fine-tuning with the augmented dataset. Work is ongoing to continue to improve generalization over real-world images.
Hello everybody. May I introduce myself? I am Tanle postdoc intern at UQAM University, Montreal, Canada, with Professor Fasia Sada. Today I am pleased to present our research on low-resource neural machine translation, the case and challenges of inuttitude. In this work, we propose a new method of morphologically motivated segmentation for inuttitude, and we view also our first neural machine translation for English inuttitude. Our experiments show the promising result. Future work will focus on adding more annotated data and domain-specific features in order to improve the segmentation model accuracy. We are pleased to share and discuss with you our work. For more information, please see our poster and contact our team. Thank you for your attention.
Hi everyone. Today we present a paper about delivering reproducible research. As part of the ReproLang challenge at EREC 2020, we reproduced experiments of Hartek et al., which is a robust self-learning method for fully unsupervised cross-lingual mapping of word embeddings. Not only we've been able to reproduce the original results with a negligible difference, we also assessed the algorithm's robustness with different languages not introduced in the original paper. Furthermore, we introduced several recommendations and tools regarding the guidelines researchers should follow in order to fully replicate one's experiments. We believe that this work is one more step for the community towards a 100% reproducible research. Thanks for listening, and we look forward to meeting you at MAIS 2020.
Hello, I would like to introduce myself. Balaini Bilal, PhD student at UQAM University with Professor Project Admin. I am honored to present our poster with the title Toward an Emotional Driven Natural Language Area. In our work, we focus only in the emotional intelligence considered like a key factor in dialogue generation and the conversational agent. First of all, our contribution consists here. We simulate the emotional factor by reading complex emotions in the dialogue. Second, we predict the internal state of emotion for our agent. Finally, we create a new architecture to simulate the conversation. For the experimentation, we compare our system by two methods with the state-of-the-art of the automatic metrics and the human evaluation. Thank you for your attention.
Hello, my name is Giancarlo Kirk. I'm presenting our work on learning long-term dependencies using cognitive inductive biases in self-attention RNN. Since self-attention RNNs have quadratic computational complexity, our paper tries to answer the following question. How can we sparsify attention in RNNs in order to maximally reduce computational complexity memory usage while simultaneously maintaining good gradient propagation over large timescales? We achieve this by splitting memory into short-term buffer and long-term memory. The fixed-size short-term buffer is used to decide whether a given state is relevant enough to be stored in long-term memory or whether it should be erased forever. This achieves linear computational complexity. This idea is inspired by the cognitive process of memory consolidation, which is the transfer of memory tokens from short-term to long-term memory. We tested this method on transfer copy, denoise, as well as mini-grid RL and outperformed existing baselines such as SAB and full self-attention RNN. Finally, our method strikes an optimal trade-off between stable gradient propagation and memory usage. Thank you.
Hello everyone, my name is Rihab Al-Hassani and I'm going to present our work entitled Developing a Core Set of Mobility Domains Among Individuals with Acquired Brain Injury Using Natural Language Processing. This work has been done in collaboration with Matthew Godbout, Audrey Durant, and my PhD supervisor, Sarah Ahmed. The goal of this study, first, identify domains of mobility presented in the scientific literature. Second, automatically regroup domains in clusters that occur in a high frequency together. The methodology includes 5 steps. The first 2 steps resulted in extracting domains and items from measures in the literature. Steps 3 and 4 then clusters domain and items based on neural network processing of literature on mobility and acquired brain injury and reduce embedding dimensions. Step 5, identify a core outcome set. The best grouping according to experts recognized 6 clusters. Overall, our methodology improved the performance of the model. We'll be happy to discuss our work in more details at the poster session.
Hello, my name is Vasilios Lioutas from Carleton University. Today I'm going to talk about sequence modeling with time-aware large-kernel convolutions. This work is published in ICML 2020. As we know, sequence modeling is a fundamental and challenging task in machine learning. It's a process of learning how to combine different time steps to form more abstract representations. Perhaps the most well-known neural architecture for sequence modeling is the recurrent neural network. Most recently, non-autoregressive methods such as convolution and self-attention-based approaches achieve state-of-the-art results in numerous tasks. If we look at the time complexity, self-attention, due to the pairwise similarity between all the time steps, it has a quadratic time complexity with respect to the sequence length. RNNs have linear complexity, but they cannot parallelize, and CNNs have linear complexity, which depends on the kernel size, which is given as a hyperparameter. We propose a new sequence modeling method, which we call toconvolutions. Our method is not based on self-attention and has a true linear complexity with respect to the sequence length. It utilizes an adaptive multi-headed summation convolution kernel, which can be illustrated as in the following image. We saw in the experiments that we conducted in machine translation, abstracted summarization, and language modeling that our method can get results that are on par with self-attention and convolution-based methods.
Hello everyone, my name is Marwan Yassin, and on the 11th of September 2020, my colleague David Boschman and I will be presenting our work on multinational address parsing as part of the Montréal A.I Symposium. Address parsing aims at identifying the different elements of an address, such as a street number or a postal code. During our postal session, we'll be discussing the design and implementation of our recurrent neural network architecture and how we employed both word embeddings as well as subword embeddings to achieve state-of-the-art results on holdout training data and good results in a zero-shot setting. So stay tuned and come pay us a visit on the 11th of September at the Montréal A.I Symposium.
My name is Emmy Baylor, and I'm presenting my joint work with Sasha Lucioni entitled SUSPERT, Identifying Climate Change in Financial Disclosures Using Question Answering. Sustainability reports are reports released by companies that discuss anything and hopefully everything relating to their company and the environment. In the past few years, there has been an increase in the number of sustainability reports produced by companies, which is great. However, this means more work for the people analyzing the reports, which usually happens by hand. This is not so great. The goal of our work is to use natural language processing to create a custom tool allowing more efficient analysis of financial reports. We utilize the 2-sentence capabilities of BERT-based models and feed in first a question taken from a set of 14 predetermined questions, and then a potential answer taken from the document being analyzed. The task is to predict whether or not the potential answer truly does answer the given question. We fine-tune a variety of BERT and Roberta models for the task on a small, highly unbalanced dataset of hand-labeled financial reports. As you can see, our results are fairly good, but neither model generalizes very well. While it does worse overall, we chose to use Roberta Base because it is a less computationally expensive and more environmentally friendly model.
We developed the COVID-19 question answering system to alleviate pressure on government helplines. Users enter free-form questions and obtain, whenever available, relevant up-to-date answers from the COVID-19 FAQ section of the Quebec.ca government website. Our Q&A system is designed to deal with regular data updates to ensure accurate information is always provided. The data is therefore non-stationary and not identically distributed. Our dataset consists primarily of paraphrases of the FAQ questions collected through Mechanical Turk which mimic user questions. Our model consists of 2 main components. a fine-tuned BERT model that ranks all COVID-19 FAQ questions according to their relevance with the user's question, and an out-of-distribution detector that determines which questions can be answered given the FAQ contents. The performance of the system is higher on test examples sampled from the same distribution as the training data, which we attribute to the non-stationarity of the data. While initial results are promising, we hypothesize that overall performance can be improved by capturing user feedback and using it to refine our model.
Thanks for checking out big players tweeting about global warming. We define these big players as high activity users with respect to the tweets and the retweets they send out and how often they're retweeted or mentioned by other users. We have a data set with over 400,000 tweets with the hashtag global warming. We represent them as emotion vectors, and we use the emotion expressed by these high activity users to predict variation in the levels of emotion in the general Twitter community. And we do this with respect to two ways of looking at the period. Here, if we're predicting within a period, we see that the big players are not performing better than a random reference group. However, if we predict in the months after the period, after the training set, we see we get this curve defined by big player set size, which does have predictive capability for fear and also for anger. Check out the poster. Thank you.
So this was our last block of poster spotlights. I hope that you have been enjoying the symposium so far. I really need to thank again our great keynote speakers and panelists, Natalie Schluter, Zach Lipton, and Irina Risch. I also want to thank Abhishek Gupta for moderating the panel and everyone who submitted questions and participated, contributing to the success of the event. And I want to thank again our sponsors for making the Montreal A.I Symposium possible. I've heard that the sponsors are going to post hiring job offerings at the booths later during the poster session and social in Gathertown, so you should check them out. I've also heard that a sponsor might even have a DJ for the occasion, so you should really tour the sponsors' booths. And finally, of course, I want to thank again all the co-organizers without whom the event would not have been possible. So with this, we're now ready to move to the virtual poster session and virtual social in Gathertown. You have received the link to the Gathertown from Eventbrite. This is the same as for the welcoming coffee this morning. And we're also going to put it here in the chat in case you've lost it. So please come join us with all the poster presenters and sponsors right now in Gathertown. See you.